In rooms colder than deep space, quantum computers are spitting out answers no classical machine can realistically check, results that seem to arrive from nowhere. If physics in one universe can't reproduce the path to those numbers, then what exactly is doing the work? Are these machines just exploiting quantum rules, or are they borrowing computation from parallel realities? And what does that imply about our cosmos? A new kind of machine is forcing physics to testify under oath, and the testimony is not comforting. We are building devices that don't merely model nature, they compel nature to compute. What follows is not a story about faster chips or clever code, but about the cost of knowing. Each run ends as ordinary bits on a screen, yet the process that produces them unfolds in a space of possibilities so vast that our usual intuitions fail to map it. To keep that fragile process alive, engineers build fortresses against the world, refrigerators, filters, shields, timing systems, and materials tuned to silence. Even then, the environment presses in like a relentless interrogator, stealing phase, scattering correlations, turning quantum promise into classical noise. And still, the machines respond with patterns that are stubbornly specific, statistically sharp, and repeatable. The unsettling tension is not whether the answers exist, but what must be true of reality for those answers to be reached at all. Because the deeper we go, the less verification means what it used to mean. At small scales, we can check everything. At larger scales, we can only test fingerprints, hardness arguments, noise signatures, and consistency under controlled sabotage. That shift is where philosophy stops being optional and becomes operational. If a computation cannot be practically reproduced by any classical description we can run, then the line between prediction and inference begins to blur, along with the line between one coherent world and many mutually inaccessible records. This documentary follows the trail from laboratory discipline to cosmic implication, tracing how superposition becomes engineered interference and how entanglement becomes a resource that survives distance. Along the way, we will meet the interpretations that try to stay politely abstract, until quantum hardware made them feel uncomfortably concrete. We will not pretend these machines have settled the most controversial questions, because they have not. But they have made one conclusion unavoidable. The quantum structure of reality is not a metaphor, and it can be stabilized, scaled, and used, whether or not our preferred story of the universe survives the process. So as the visuals descend into wiring looms, vacuum chambers, and the quiet glow of cryogenic stages, keep one thought in mind. We are not simply watching technology advance. We are watching the definition of one world strain under an experiment we can finally build. Before we begin, let us know in the comments below where in the world you're watching from and what time it is there. Now, settle in for a journey. We begin in the cold hum of the lab, then rewind through the experiments that broke classical certainty, before returning to the edge where verification itself becomes a frontier. And when the journey widens to security, institutions, and cosmology, the question is no longer academic, it is architectural. In a sealed room, the loudest sound is a low electrical hum, steady as a distant transformer. The air feels ordinary, almost office dry, but the physics inside is not. Behind shielding and interlocks, a machine runs colder than deep space, colder than the cosmic microwave background that fills the universe. It is not built to be fast in the usual way, with fans and heat sinks and higher clock rates. It is built to keep reality from touching it, because even a gentle touch can erase the computation. Quantum computers live inside dilution refrigerators, where temperatures fall to millikelvin and sometimes below 10,000ths of a degree, above absolute zero. At that scale, heat is not comfort, and it is not merely a nuisance. Heat is random motion that becomes electrical noise, and noise flips fragile quantum states into ordinary bits. Engineers fight vibration that shakes components by nanometers, stray photons that slip down a cable like stowaways, magnetic fields that drift with elevator motors, and cosmic rays that punch through shielding with indifferent energy. Every cable is filtered with attenuators and low-pass stages, every surface is grounded to tame static charge, and every material is chosen for what it does at cryogenic temperatures. The lab becomes an artificial universe with rules enforced by hardware, and the price of those rules is constant vigilance. Look closely at the refrigerator, and it resembles a metallic tree hung with braided coaxial lines. Each stage is a colder ring inside the next, and each ring is a checkpoint. At room temperature, signals are loud and messy, but at millikelvin they must arrive as whispers, so the wiring descends through thermal anchors that bleed away heat, and through filters that remove radio frequency trash. Even the vacuum can matter, because residual gas molecules can carry heat and collide with sensitive parts. The machine is not just cold, it is quiet. Quiet in vibration, quiet in light, quiet in magnetism. This is the first mystery of quantum computing. To compute, the device must be isolated from the world, because the world is a measurement machine. Yet to read an answer, it must interact with the world, because answers must become voltages and numbers and files. The entire architecture is a compromise between protection and measurement, and that compromise is engineered down to the shape of a connector. The machine is both a fortress and a microphone, listening for a signal it must not disturb. Different teams build different fortresses, and each fortress reflects a different philosophy about what is easiest to control. Superconducting qubits sit on chips, patterned like tiny circuits, cooled until resistance vanishes and currents can flow without dissipation. Microwave pulses nudge them, rotate them, and entangle them, and the timing of those pulses is measured in nanoseconds. Trapped ion systems suspend charged atoms in electromagnetic fields, then use lasers to control motion and internal states with exquisite spectral precision. Photonic approaches guide single photons through interferometers, where paths and phases do the work, and where loss is the enemy that quietly drains probability away. Each platform is a different way to hold a quantum system still enough to compute, and each one pays for stability in its own currency. Superconducting devices, for example, are often built from Josephson junctions, thin insulating barriers that let paired electrons tunnel in a way that behaves like a nonlinear inductor. That nonlinearity is crucial because it separates energy levels so the qubit can be addressed without accidentally exciting a ladder of unwanted states. The chip sits inside a package designed like a miniature cave, and the cave is designed to kill resonances that could feed back into the qubit. Trapped ions, by contrast, turn the qubits into literal objects you can picture, a line of glowing points in a vacuum chamber. Yet even there, the glow is a controlled illusion, produced by carefully tuned light that both cools and reads the ions. Photonics can look cleanest on paper, but in practice it demands alignment, phase stability, and detectors that can register single photons without adding their own false clicks. The common demand is control beyond intuition, because qubits cannot be treated like switches that are either on or off. They are closer to musical instruments that must stay in tune while an orchestra plays around them. A slight drift in frequency, a stray reflection from an impedance mismatch, a tiny timing error between pulses can ruin a computation. Noise is not only random, it can be structured, and structured noise is harder to average away, so the lab is designed to make the environment simple, even if the machinery looks baroque. It is engineered emptiness, built so that the remaining interactions are the ones we intended. The second mystery is what these machines claim to do, once the cold and the shielding finally hold. They run algorithms that for certain tasks seem to outrun classical computers, not by a small margin, but by a gap that grows with every added qubit, like an opening door. The promise is not just speed, as if we were shaving seconds off a calculation. The promise is access to computations that are effectively unreachable by classical simulation, because the description of the system itself becomes too large to track. To understand why, we need a basic picture of quantum information, and we need to keep it grounded in something speakable. A classical bit stores one of two values, and it can be copied and checked without changing it. A qubit stores a state that can be a combination of both, described by complex amplitudes whose phases matter as much as their sizes. Superposition means many potential outcomes coexist in one description, like overlapping notes in a chord. It does not mean we see all outcomes at once, as if the machine hands us every answer. It means the system evolves as if all those possibilities matter, until measurement forces one outcome into the classical record. Entanglement is the next ingredient, and it is where the intuition begins to fail in a productive way. It links qubits so their outcomes are correlated beyond any classical shared plan, even when the qubits are separated and never exchange a signal during the measurement. Measure one, and the statistics of the other change instantly in the description, because the pair is described by one joint state. No signal is sent that breaks relativity, and no usable message travels faster than light. The connection is in the mathematics of the shared wave function, not in a hidden telegram. Entanglement makes the whole system more than a list of parts, and it makes the state something you cannot assign to each qubit independently. Interference is how the machine uses those possibilities, and it is the closest thing quantum computing has to a steering wheel. Quantum amplitudes can add or cancel like waves on water, and the phase between them decides whether they reinforce or erase. A good algorithm arranges phases so wrong paths cancel out, and right paths accumulate weight. It pushes probability toward useful answers without checking every option directly, because the checking is replaced by wave-like cancellation. The computation is not brute force, and it is not magic. It is choreography, performed in a space where minus signs and angles are physical resources. These three terms sound abstract, but they point to a concrete scaling problem that hits like a wall. A system of n qubits is described by two uncomplex amplitudes, and each amplitude is a number that must be tracked with enough precision to predict interference. That number doubles with each qubit added, which is a gentle sentence hiding an explosive curve. At 10 qubits, the description is manageable, and you can simulate it on a laptop. At 50 qubits, it strains the best supercomputers, because memory and compute time become the limiting reagents. At 100 qubits, it becomes a storage and time nightmare, and even writing down the state becomes an act of fantasy. This is what beyond classical reach means in practice, and it is more sober than the slogans. It does not mean classical physics is wrong, and it does not mean the classical computer is obsolete. It means classical simulation becomes infeasible at scale, because the resources required grow so quickly that verification becomes an engineering impossibility. Even if the laws are known, the bookkeeping explodes, and bookkeeping is what simulation really is. The difficulty is not philosophical at first, it is logistical. Here the documentary's tension begins. A quantum computer can output a string of bits after a run, and that output looks ordinary, like any digital result. It arrives as a histogram on a screen, a list of counts, a file you can email. But the process that produced it may be too complex to reproduce classically, even if you know every gate you asked for. If we cannot simulate the full quantum state, we cannot independently check every step as we would in ordinary software. We are asked to trust a machine we built using a theory we test in a regime we cannot fully audit. Scientists do not accept magic, and they do not accept black boxes without pressure testing them. They build cross-checks that do not require full simulation, and they treat the device like an experimental apparatus that must be calibrated and challenged. They test smaller versions that are classically tractable, then scale up while watching which error rates drift and which correlations survive. They compare different devices and different noise models, because noise has fingerprints, and those fingerprints can betray a classical imposter. They use statistical signatures that are hard to fake, such as patterns expected from interference rather than from simple randomness. They design protocols where cheating would require the same exponential resources, which makes faking it nearly as hard as doing it. But the uncomfortable fact remains, and it grows more uncomfortable as systems scale. Verification becomes probabilistic and indirect, more like judging a distant star by its spectrum than inspecting a machine part under a microscope. You can test consistency across many runs, and you can look for deviations that signal decoherence or crosstalk. Yet you cannot always compute the exact distribution you expect, because that computation is the thing you are trying to surpass. The tests become a web of constraints, and the web can be strong without being complete. This is not a minor technical detail because it changes what a result means and what kind of confidence is possible. In classical computing, you can rerun a program and trace the logic, and you can often isolate a bug to a line of code. In many experiments, you can model the apparatus and predict outcomes with controllable error bars. With large quantum devices, the full prediction is the thing you cannot do, at least not by brute calculation. The machine becomes part of the evidence, and the evidence includes the machine's own behavior. So what counts as scientific discovery in this regime, when the object and the proof begin to blur? If a device produces a distribution that matches quantum theory, that supports the theory, and it supports the engineering that kept coherence alive. Yet if the distribution is too complex to compute classically, the match cannot be checked point by point, like verifying every pixel in a massive image. We rely on consistency, on partial tests, on theoretical arguments about hardness, and on the absence of classical explanations that fit the same data. The standard of proof shifts from exact reproduction to structured confidence, and that shift must be acknowledged rather than hidden. That shift invites a deeper question, and it is the kind that keeps a lab quiet after hours. How do we know the machine is not cheating? Not in the human sense, but in the physical sense. Could there be hidden classical shortcuts in the hardware, like unintended couplings that reduce the true complexity? Could noise mimic the signature of quantum advantage, producing outputs that look hard while actually being degraded? Could our benchmarks be too narrow, rewarding tricks rather than genuine quantum computation, the way a test can be gamed by teaching to the questions? These are active debates, not settled slogans, and the debates are part of the science. Even if the device is honest, another question waits behind it, quieter and stranger. What is the computation actually doing, in any picture we can hold in our minds? In the lab, we send pulses and read voltages, and those voltages are amplified through room temperature electronics that have no idea what they are witnessing. In the mathematics, we evolve a state vector in a Hilbert space, rotating it with unitary operations that preserve total probability. The state vector is not a picture of tiny balls moving through tiny gears. It is a rule for predicting outcomes, and it is a bookkeeping device that somehow predicts the world with ruthless accuracy. When the number of amplitudes becomes astronomical, the rule begins to feel like it describes something real, even if we cannot visualize it. It feels like a vast hidden structure that the machine is navigating, a landscape of phases and correlations that cannot be compressed into ordinary space. The refrigerator becomes, in a sense, a portal to that landscape, because it forces the abstract object to behave consistently. We can deny that the wave function is real, but the hardware behaves as if it is obeying a real constraint. The question becomes less about belief and more about what kind of description earns the right to be called physical. This is where the cosmological angle enters. Computation is physical, and that statement has a history that runs through thermodynamics and information theory. Every bit flip costs energy, every memory has a material substrate, and every clock is a physical process that must resist noise. Even the act of erasing information has a minimum thermodynamic price, a reminder that logic is not free. If computation is constrained by physics, then a new kind of computer is a new kind of physical experiment. Quantum computing is not just technology. It is a probe of the universe's rulebook, built from the same ingredients as atoms and light. Quantum theory has always worked, but it often felt like a description we used from the outside, like a set of equations we consulted. We predicted spectra, built transistors, and measured probabilities, and the weirdness stayed politely behind the glass. Now we're building devices that use superposition and entanglement as resources, the way a steam engine uses pressure. We are not merely observing the rulebook, we're applying it deliberately, step by step, as an engine. The difference is subtle in words, but enormous in practice, because it turns interpretation into engineering. That makes the verification problem feel larger than computing, and it gives the hum in the lab a philosophical edge. If a quantum device performs a task no classical machine can feasibly reproduce, then the universe is doing something that resists classical description, at least in any direct computational mirror. It is still the same universe, and it still obeys the same equations we write down. But our ability to track it, to duplicate it in silico, is limited by exponential growth. The gap is not just computational, it is epistemic, a limit on what can be known by reconstruction. Some physicists interpret that gap in a radical way, and the radicalism is older than the hardware. The many worlds interpretation says the wave function is real and never collapses, and that measurement branches the universe into outcomes, each realized in a different branch. In this view, a quantum computation explores many branches, and interference recombines them, selecting a result the way a lens focuses light. The speed-up is not from cleverness alone, it is from parallelism across realities, with phases acting like a voting system. It is a story that fits the math cleanly, and it unsettles people for exactly that reason. Other interpretations reject that picture, and they do so without changing a single experimental prediction. They keep one world and treat the wave function as information, or as a tool for organizing expectations about measurement results. They explain quantum speed-ups through entanglement structure and interference, without extra universes hidden behind the equations. They point out that many worlds does not change predictions, and they argue it adds metaphysics, not mechanism. The disagreement is not about what the device does, but about what the mathematics is allowed to mean. But quantum computers sharpen the argument, because they take the abstract formalism and force it into hardware that must survive contact with the real world. They make the wave function feel less like a spreadsheet and more like a machine room, filled with cables and attenuators and carefully timed pulses. When a device with dozens or hundreds of qubits behaves as if it carries 2 amplitudes, we face a choice about language and about ontology. Either that structure is a convenient fiction that nevertheless predicts perfectly, or it is a real part of what exists, expressed in a form our senses did not evolve to grasp. The machine does not settle the debate, but it makes the debate harder to ignore. The terrifying possibility is not that quantum computers fail, because failure would be familiar and explainable. The terrifying possibility is that they succeed too well, and that success becomes routine. If they keep scaling, they will routinely produce outputs that no classical method can verify in detail, not because we are lazy, but because the resources do not exist. We will have instruments that work, and theories that predict, and results that cannot be fully checked by any other means. We will be living with a new category of knowledge, one that depends on controlled trust in a physical process. This chapter begins in the cold because cold is the price of coherence, and coherence is the price of meaning. The hum you hear is the cost of holding a quantum state together, paid in power supplies, compressors, and quiet mechanical discipline. The cables and filters are not accessories, and they are not aesthetic clutter. They are the boundary between our warm world and a controlled quantum one, where even a stray thermal photon can act like an unwanted observer. Inside that boundary, computation becomes an experiment on reality's hidden degrees of freedom, performed in a darkness colder than space. The next step is to define what it means to trust such an experiment, without pretending the trust is absolute. We need to see how scientists test quantum devices without simulating them, and how they separate genuine quantum behavior from clever classical lookalikes. We need to understand what hardness assumptions really claim, and what they do not, because hard is a statement about resources, not about possibility. And we need to ask whether the many-world story is an explanation, a metaphor, or a warning about how far our intuitions can stretch. Because if the universe computes in a way we cannot classically track, then our machines are not just tools, and they are not just faster calculators. They are witnesses, built to preserve a fragile process long enough to speak. And the testimony they give may force us to rethink what a single reality even means, or whether single is the wrong category. The hum follows us out of the lab, not as a sound, but as a question. We leave the cold lab with one question that will not warm up, no matter how bright the hallway lights feel. When the answer cannot be independently reproduced, what exactly have we learned, and what kind of confidence have we earned? And if the computation is real, where did it happen? In the chip, in the mathematics, or in the universe that makes both possible? We step back from the refrigerator and into the argument that made it necessary. Quantum computers did not invent quantum weirdness. They industrialized a set of experimental facts that refused classical explanation for a century. The lab around us looks ordinary. Cables, racks, blinking status lights. Yet the physics inside is anything but ordinary. The refrigerator is a visual metaphor for restraint, because quantum behavior survives only when noise is held at bay. Every shielded wire and filtered signal is there to protect correlations that classical intuition would rather deny. At the start, the crisis looked like bookkeeping, not metaphysics. In 1900, Max Planck fit blackbody radiation by quantizing energy exchange. He treated energy as arriving in discrete packets, proportional to frequency, because the math otherwise exploded at short wavelengths. What began as a technical fix quietly introduced a constant h that would later set the scale of the microscopic world. In the archival drawings of glowing furnaces and spectral curves, the problem is almost mundane. A hot object should radiate smoothly across colours, yet classical theory predicted an ultraviolet catastrophe, a runaway flood of high-frequency light. Planck's quantization cut off that runaway, and the curve finally matched what instruments saw. Nature, it seemed, was not infinitely divisible in its exchanges. Albert Einstein pushed the idea further in 1905 with the photoelectric effect. Light behaved like particles when it hit metal, and classical waves could not explain the sharp threshold. Below a certain frequency, no electrons were ejected no matter how intense the light was. Above it, electrons popped free immediately, as if struck by discrete blows. Einstein's photons were not a philosophical flourish. They explained why energy depended on colour rather than brightness, and why the emitted electrons carried a kinetic energy that rose linearly with frequency. The quantum was no longer a mathematical convenience, it was a physical demand, enforced by the clean edges of experimental data. Niels Bohr then built an atom that only allowed certain orbits and energies. The model was patched together, but it predicted spectral lines with unnerving accuracy. Hydrogen's emitted colours, measured as narrow lines, matched Bohr's quantized energy differences. The message was clear. Microscopic systems did not permit continuous classical motion. In the imagined visuals of early spectroscopy, the atom becomes a tiny instrument. It does not sing every note, only selected ones, and the gaps are as important as the notes themselves. Bohr's picture still used planetary language, yet it smuggled in a deeper rule. The electron was allowed to be stable only when its angular momentum came in discrete units of h. By the mid-1920s, the patchwork became a formal theory. Heisenberg's matrix mechanics and Schrödinger's wave mechanics agreed on predictions. They also agreed on something more disturbing. The theory did not predict single outcomes, only probabilities. Heisenberg built his mechanics from what could be observed, spectral transitions and measurable quantities, then discovered that the algebra of those quantities refused to commute. Schrödinger, by contrast, wrote a wave equation that looked comfortingly continuous, like ripples on water. Yet the two approaches were mathematically equivalent, and that equivalence made the strangeness harder to dismiss. Different languages, same unsettling rules. This was not a failure of instruments in early laboratories. It was built into the equations as a rule, not a temporary ignorance. Even with perfect preparation, the theory only gave a distribution of possible results. The uncertainty principle was not a confession of clumsy measurement. It was a statement about what the world permits, even in principle. Born's rule turned the wave function into a probability machine. The wave function evolved smoothly, but measurement produced discrete outcomes. The equations described a continuous story. The lab recorded a sudden jump. In a clean animation, the wave function spreads like a translucent cloud, then snaps to a single dot when a detector clicks. That click is not merely a human observation. It is a physical interaction, an exchange of energy and information that leaves a durable record in the apparatus. The puzzle is that the formalism contains both the smooth evolution and the abrupt event, without saying exactly how one becomes the other. That jump became the measurement problem. If the wave function is real, why does it appear to collapse? If it is only information, what physical process updates it? Either way, the theory worked while refusing a comfortable narrative. The success was practical, but the story felt incomplete, like a map with a blank region labelled "Here be dragons." Einstein's objection was not that quantum mechanics was inaccurate. His objection was that it felt incomplete. He suspected hidden variables, extra facts beneath the wave function, that would restore certainty without changing statistics. He wanted a deeper description that would make probabilities look like ignorance again, the way they do in classical physics. In 1935, Einstein, Podolsky and Rosen sharpened the discomfort into a paradox. They described two particles prepared in a joint state, then separated by a large distance. Quantum mechanics predicted perfect correlations between their measurements. The unsettling part was not correlation itself, but correlation without a shared local story. If one measurement instantly fixed the other's outcome, it sounded like faster-than-light influence. If no influence travelled, it sounded like the outcomes were predetermined. EPR argued that quantum mechanics must be missing something real. Their paper was carefully worded, almost polite, yet it was a direct challenge. A complete physical theory, they claimed, should not require spooky coordination across space. Bohr replied that EPR demanded an impossible kind of classical description. He insisted that measurement context matters, and that quantum properties are not simply revealed. What counts as the same property, Bohr argued, depends on the whole experimental arrangement. The debate became a stalemate in words. It needed a theorem, because rhetoric could not settle what counted as real. John Bell provided that theorem in 1964. He asked a simple question with lethal consequences for classical intuition. Can hidden variables reproduce quantum correlations while respecting locality? Bell's genius was to turn metaphysical discomfort into a quantitative inequality, something a lab could check with counting statistics. Locality means no influence travels faster than light. Hidden variables mean outcomes are fixed by pre-existing properties, not created by measurement. Bell showed that any theory with both features must satisfy certain statistical limits. Those limits do not depend on the details of the hidden variables. They follow from the structure of local causation itself. Those limits are Bell inequalities. They constrain how strongly two separated measurements can be correlated if the world is local and predetermined. Quantum mechanics predicts correlations that can exceed those limits for entangled states. The violation is not a small technicality. It is a bright line between two kinds of world models. Bell's result was not about philosophy alone. It was an engineering recipe for an experiment. Prepare entangled pairs, choose measurement settings independently, and compare the statistics across many trials. The experiment is conceptually simple, almost austere, yet it reaches into the foundations with every click of a detector. In plain language, Bell said this: if each particle carries a local instruction set for every possible measurement, then the correlations cannot be too strong. If experiments show stronger correlations, local instruction sets are impossible. The inequality is the trap. It is designed so that any local hidden variable story, no matter how clever, must fall into it. This is where the documentary's tension begins. The same entanglement that makes quantum computing powerful was first tested as a threat to common sense. Entanglement is not just two things linked. It is a single quantum state that cannot be factored into independent parts, even when the parts are far apart. The first serious assaults arrived in the 1970s and early 1980s. Alain Aspect and collaborators in France tested entangled photons and rapidly switched measurement settings. They measured polarization correlations and found clear violations of Bell inequalities. In the visuals, we see optical tables lit by dim alignment lasers, mirrors on adjustable mounts, and detectors waiting like silent ears. Aspect's experiments mattered because they reduced a key escape route. If settings are changed while photons are in flight, then one side cannot easily signal the other in time. The results still matched quantum predictions. The violations were not isolated anomalies. They appeared as stable statistical patterns repeated over many runs in a way that made excuses feel increasingly strained. But skeptics pointed to loopholes, because loopholes are where classical stories hide. The locality loophole asks whether the two measurement events were truly space-like separated. Space-like separation means there is no time for a light-speed signal to travel between them. The detection loophole asks whether missing detections bias the sample. Early photon experiments often had low detector efficiency. If only a subset of pairs is detected, a local hidden variable model can sometimes mimic quantum correlations. This is the fair sampling worry, and it haunted the field for decades. A critic could always say, perhaps the detected pairs were special, and perhaps the undetected pairs would restore classical bounds if we could see them. In the 1990s, experiments improved sources, timing, and separation. In 1998, Gregor Wise and colleagues performed a landmark test with fast random switching and large separation. They strengthened the locality side by enforcing space-like separation more strictly. The apparatus sprawled across distance, with photons sent through fibers and detectors synchronized to tight timing windows. Ways still faced the detection loophole because photon losses remained significant. Yet the pattern was consistent across many groups and many platforms. Whenever experiments approached the ideal, the correlations leaned quantum, not classical. It became less plausible that every improvement would coincidentally preserve the same mistake. Other systems attacked the detection loophole directly. Experiments with trapped ions and atoms achieved high detection efficiency because the particles could be measured reliably. Those tests violated Bell inequalities too, but their separation was often small, leaving locality less airtight. In a trap, the environment is controlled with exquisite care, but the two wings of the experiment sit too close for comfort. The field learned a hard lesson about reality. Closing one loophole often opened another, because the experimental demands pull in opposite directions. High efficiency is easier in controlled traps. Large separation is easier with photons that travel. The struggle itself became part of the story, physics not as a single decisive moment, but as a slow tightening of constraints. By the 2010s, technology and design finally allowed combined closure. So-called loophole-free Bell tests aim to close locality and detection simultaneously. They also addressed freedom of choice concerns by using fast random setting choices. The goal was not perfection, but credibility. Remove the most reasonable classical escape hatches at the same time. In 2015, multiple groups reported loophole-free violations. The Delft experiment used entangled electron spins in diamond, separated by over a kilometre, connected through entanglement swapping with photons. NIST and Vienna used high-efficiency photon systems with careful timing and random setting selection. Each setup looked different on camera, yet each was built around the same logical skeleton. The details differed, but the core logic was the same. Each side chose a measurement setting quickly and independently. Each side recorded an outcome. The statistics violated Bell inequalities by margins that matched quantum theory. The violations were not just above the line, they were above the line with error bars and timing analyses that made the classical alternatives increasingly contrived. Loophole-free does not mean metaphysics-free. It means the most practical classical escape routes were blocked at once. A local hidden variable model would need additional assumptions that feel more extreme than the quantum story it tries to avoid. The experiments do not force one interpretation, but they do force a reckoning with what must be surrendered. One escape is to abandon locality. Hidden variables could exist, but they would have to be non-local, coordinating outcomes across distance without a signal we can use. That keeps determinism but sacrifices the classical idea of separable causes. The universe would be stitched together more tightly than relativity's everyday intuition suggests, even if it still refuses to send usable messages faster than light. Another escape is to abandon measurement independence. If the setting choices are somehow correlated with the hidden variables, the inequality can be evaded. This is the superdeterminism move, and it implies that even our random choices are prearranged by deeper conditions. The unsettling question becomes personal. If the universe fixes outcomes, does it also fix which questions we think we freely ask? A third escape is to treat the wave function as a real guiding field with non-local influence. Bohmian mechanics does this explicitly. It restores definite particle positions, but it pays with instantaneous coordination across the entire configuration space. The price is hidden structure that cannot be switched off, a kind of global choreography underlying every local event. Each rescue has a cost that is not merely aesthetic. Non-locality threatens the intuitive boundary between here and there. Superdeterminism threatens the idea that experiments can test anything without conspiratorial correlations. Bohm's theory keeps predictions but imports an invisible structure that acts everywhere. The discomfort changes shape, but it does not vanish. The experiments do not tell us which interpretation to prefer. They do tell us what cannot be true at the same time. We cannot keep locality, realism in the classical sense, and the observed correlations all together. Bell's theorem is a triangle with one corner missing, and nature tells us which corner cannot be kept. This is the first impossible experiment in the modern sense. It is not impossible to perform. It is impossible to explain with a full set of classical assumptions intact. The impossibility is conceptual, not practical, and that makes it linger in the mind longer than a technical surprise. The measurement problem returns here with sharper teeth. If outcomes are not pre-existing local facts, then measurement is not passive reading. Measurement is an interaction that selects a result from a joint quantum state. The apparatus is not a neutral window. It is part of the phenomenon, leaving a record that cannot be unmade. That selection can be described as collapse, as branching, or as updating information. The mathematics stays the same, but the story changes. Quantum computers will later force us to confront which story we can engineer around. When we build devices that rely on coherent superpositions, we're forced to treat the wave function as more than a bookkeeping trick. The key point for this documentary is narrower and more concrete. Entanglement is not a metaphor. It is a reproducible resource that violates classical bounds under controlled conditions. In the lab, it shows up as synchronized statistics that no local instruction set can match, even when every classical loophole is squeezed. Bell tests show that quantum correlations are stronger than any local hidden variable plan. They show that nature respects the no signaling limit while refusing local realism. That combination is exactly what makes quantum information distinct. The correlations are too structured to be coincidence, yet too constrained to be used as a faster-than-light telegraph. It also explains why quantum theory predicts probabilities, not certainties, without apologizing. The randomness is not just ignorance of hidden local facts. The randomness is what remains when the world refuses a local predetermined script. Even when we know the state as well as physics allows, The outcome arrives as a genuine event, not a revealed secret. Physicists learned to live with that refusal because it kept paying rent. Quantum mechanics predicted spectra, chemical bonds, semiconductors, lasers, and superconductors. The same formalism that offended intuition built the modern world. The strange rules did not stay in textbooks. They became the operating system of technology, embedded in every transistor and photon detector. Yet the discomfort never disappeared, because the theory's core objects are not classical things. The wave function lives in a space of possibilities, not in ordinary three-dimensional space. Entanglement links systems in that space, not by a visible thread. What looks like two particles in the lab can be one mathematical object in the theory, spread across distant locations. Quantum computing enters as the next escalation, not a separate mystery. If entanglement produces correlations that violate classical inequalities, then it is already doing something classically unsimulable in principle. The only question is scale and control. Can we preserve those correlations across many qubits, long enough to steer them toward a useful answer? A small bell pair is a proof of concept for a much larger claim. If two qubits can exceed classical constraints, then many qubits can exceed classical bookkeeping. The exponential state space is not a slogan. It is the accounting system forced by experiments, because amplitudes must track possibilities that cannot be compressed into local classical facts. This is where the cosmological angle enters. When a quantum computer produces results beyond practical classical verification, is it merely exploiting quantum mechanics inside one universe? Or is it evidence that computation is distributed across parallel realities, as many worlds suggests? The question is not asked as a gimmick. It is asked because the formalism invites it, and because the experiments refuse to close the door. Many worlds offers one clean way to read Bell violations. The wave function never collapses, and measurement creates branches with different outcomes. Correlations arise because the branches share a single pre-measurement state, and interference history constrains what can co-occur. In that view, the spooky coordination is not a message sent across space. It is a constraint inherited from a shared origin in the wave function structure. Other interpretations keep one world and accept non-local structure or contextual outcomes. They argue that Bell violations demand weirdness, not necessarily multiple realities. The experiments decide the constraints, not the metaphysical packaging. What we can say, with confidence, is that the classical picture of independent properties carried through space is not enough. For our story, the key is what quantum computers inherit from this history. They are built to preserve entanglement across many components. They are built to steer interference across a space that classical variables cannot track efficiently. Every gate and calibration routine is an attempt to sculpt probability amplitudes without letting the environment measure the system first. Bell's theorem tells us that classical simulation is not just hard because we lack cleverness. It is hard because classical locality and hidden instructions are not the rules being used. The machine is allowed correlations that classical models must forbid. When we try to simulate it classically, we are forcing a non-classical process into a classical container, and the container overflows. So when a quantum processor begins to outrun classical verification, it is not leaping into speculation. It is extending a pattern already confirmed in Bell tests. The same non-classical structure that broke inequalities now breaks classical simulation budgets. The scale changes, but the logic rhymes, and the rhyme is written in the statistics. The first impossible experiment was a pair of particles that refused local explanation. The next impossible experiment is a device that scales that refusal into computation. If reality violates classical constraints, then machines built from reality can exploit that violation. The unsettling thought is that the machine is not cheating. It is simply obeying the deeper rules we already measured. We return to the cold lab with a different kind of unease. The refrigerator is not protecting delicate magic. It is protecting the exact correlations that experiments forced us to accept. Inside, qubits are kept cold enough that thermal noise cannot drown out phase relationships, and quiet enough that the environment cannot steal which path information. And the central question tightens. When the outputs become too complex to reproduce classically, are we seeing one universe compute in a way we cannot mirror? Or are we watching many outcomes coexist long enough to do work, then collapse into one record? If the answer is we cannot tell, what does it mean to build technology on a process we cannot narrate in a single classical story? Chapter 3 follows the consequences into engineering. It asks how we verify quantum behavior when full simulation fails. It asks what counts as evidence when the device itself is the only practical witness. In that next step, the philosophical unease becomes a practical design constraint, because verification, like measurement, is where the theory bites hardest. The refrigerator's quiet is not just engineering discipline, and it is not just comfort for the technician standing nearby. It is the price of keeping a calculation spread out, coherent, and vulnerable to interference. In the lab, silence has a temperature, millikelvin cold, and it has a meaning. Fewer vibrations, fewer stray photons, fewer chances for the outside world to listen in. Visually, it begins with the hardware. A tall dilution refrigerator hangs like a metallic chandelier, layered in gold and copper shields, with cables descending in careful bundles. Each stage is a colder ring, and each ring is a filter against noise. The machine looks like plumbing, but it behaves like a boundary between everyday thermodynamics and a more delicate regime. In classical computing, information sits in bits that are either 0 or 1, and those values can be copied, read, and refreshed. In quantum computing, information sits in a state vector whose entries are complex amplitudes. That difference is not cosmetic because it changes what it means to store information and what it means to lose it. A single qubit is not a coin that is secretly heads or tails waiting for us to peek. It is a two-dimensional vector, written as A0 plus P0 with A and V complex numbers. The symbols ot0 and /1 are not physical labels on a tiny switch. They are basis states, a coordinate system for describing what we can later measure. Those numbers are not probabilities, even though they eventually become probabilities when we look. They are probability amplitudes, and the probabilities appear only after squaring magnitudes and summing where paths overlap. The rule is strict. Are 2 plus? 2 must equal 1, because the total probability of getting some outcome cannot drift. Complex numbers matter here, because they carry both magnitude and phase is where quantum behavior hides. The phase of an amplitude is not decoration, and it is not an optional mathematical flourish. Phase is the handle that later gates grab, because phase decides whether contributions reinforce or cancel. On screen, phase can be drawn as an arrow on a circle, rotating like a compass needle on the complex plane. 2 arrows can point the same way and add, or they can point opposite ways and subtract. That simple geometry becomes a physical prediction when the qubit is measured. This is why superposition is more than a slogan about being in 2 states at once, which is a phrase that invites confusion. It is a precise linear structure that preserves phase relationships over time. The qubit is not half 0 and half 1 in the everyday sense. It is a vector whose direction encodes what future operations can do. A classical probability distribution can describe uncertainty about a hidden definite state, like a card face down on a table. A quantum state describes a system that has no single definite classical state to be uncertain about. The difference sounds philosophical, until you see what happens when alternatives are recombined. That difference stays invisible if you only look at one measurement outcome, because any single run is just one bit of data. It becomes unavoidable when you recombine possibilities and watch interference reshape the statistics. Quantum theory is built to predict patterns across many trials, and those patterns carry the signature of phase. Interference is the first place the math becomes physical, because it turns invisible angles into visible frequencies. 2 amplitudes can add to make an outcome more likely, or add to make it vanish. The vanishing is the shock. An outcome can be perfectly allowed by classical reasoning, and yet be erased by cancellation. In a double-slit experiment, the pattern is not explained by ignorance about which slit, and it is not rescued by a hidden coin flip. The pattern is explained by amplitudes travelling both ways, then interfering. Bright bands appear where phases line up, and dark bands appear where phases oppose. An image that looks like ripples yet lands as discrete clicks. Historically, this was not a gentle conclusion. Early quantum pioneers argued over what the wave meant, because it behaved like a wave but arrived like a particle. The mathematics that survived, complex amplitudes evolving linearly, was the part that kept predicting the interference fringes with brutal accuracy. Quantum algorithms use the same logic but with more slits than any physical screen could hold. Gates split, rotate, and recombine amplitudes inside an abstract space. Instead of 2 paths through 2 slits, there are paths through computational steps, and their phases accumulate like optical path lengths. To say the system explores many possibilities is partly true, but dangerously incomplete. The system explores a single vector that contains many components with phases. The components are not independent stories because a later operation can bring them back together and make them cancel. A useful superposition is not a list of parallel classical worlds running independently, each doing its own private work. It is one object whose components can cancel each other, which classical parallelism cannot do. Classical threads can race, but they cannot annihilate a wrong answer by subtracting it from itself. This is where the documentary's tension begins. The state is easy to write as a formula, but it becomes impossible to store as a classical record. The very thing that makes the description compact on paper, linear algebra, makes the full content explode when you try to enumerate it. For in qubits, the state vector has two Horn complex amplitudes, one for each basis string from Bort to Rundstrom to Kell-11, and each added qubit doubles the bookkeeping required to predict what the device will do. The doubling is not a metaphor, and it does not slow down to be kind. The growth is not a metaphor. It is the literal dimension of the Hilbert space needed to represent the most general quantum state. Hilbert space is not a place the qubits sit inside. It is the mathematical arena where their correlations live, and where unitary gates act like rotations. At n equals 10, 2 phi is Thalos 24, and simulation is trivial on a laptop. At n equals 30, it is about 1 billion, and simulation becomes a serious project. At that scale, you do not just run out of time, you run out of memory bandwidth and patience. At n equals 50, 2n is over 1 quadrillion, and memory becomes the bottleneck even before time does. If you store each complex amplitude in double precision, you need tens of petabytes just to hold the vector once. At n equals 100, the numbers stop fitting intuition, and even the language of big starts to feel childish. A classical simulator must track those amplitudes with enough precision to preserve phase, because phase errors behave like wrong turns in a maze. Small numerical errors can fake or destroy interference, so approximation is treacherous. You can compress magnitudes and still lose the computation, because the answer is often encoded in delicate cancellations. This is why quantum advantage is not only about speed, which is the headline people remember, it is about representational capacity, because the natural description of the state explodes exponentially. The device is not merely faster at a known task, it is operating in a space that refuses to be written down in full. Researchers can often simulate special cases efficiently, and that is not a failure of quantum theory. They exploit structure, low entanglement, symmetry, or noise that collapses the state into something compressible. In those regimes, the vector is large in principle, but it is redundant in practice. But the whole point of a quantum processor is to avoid those compressions when the algorithm needs the hard regime. It tries to stay in the hard regime where no short classical description is known. That is why the refrigerator is not just cold, but stable, because instability is a shortcut back to compressibility. When people say a quantum computer holds two states at once, they are pointing at this vector size, and they are reaching for a metaphor. The phrase misleads because it suggests two separate classical registers, each filled with a readable answer. The reality is stranger and less convenient. The device does not contain two unreadable answers, waiting on shelves like files in an archive. It contains two amplitudes that can be rotated so that most answers cancel, and a few survive. What survives is not selected by inspection, but by interference engineered through the circuit. That cancellation is the engine, and it is why phase is treated like a resource. Without interference, superposition is just spread out probability, and measurement would return a random option with no advantage. The algorithm succeeds only when it shapes the phase landscape so that randomness is biased toward the desired structure. A quantum circuit is a sequence of unitary operations, and unitary is a promise of reversibility. Each unitary is a reversible rotation in Hilbert space, designed to sculpt the amplitude landscape. Reversible does not mean easy to undo in practice, but it means information is not discarded until measurement. The goal is not to evaluate every candidate and then choose the best, which is how classical search feels. The goal is to arrange phases so that wrong candidates interfere destructively across many paths. Then the remaining candidates interfere constructively, and their probabilities rise. The algorithm is a choreography of plus signs and minus signs that become measurable frequencies, and the choreography must be precise. If the phase is off by a little, the cancellation is incomplete, and wrong answers leak back in. In that sense, quantum computing is not only computation, it is controlled wave mechanics. Grover's search is the simplest parable because it exposes the mechanism without hiding behind heavy mathematics. It marks a target state with a phase flip, then uses a diffusion step to rotate amplitude toward that target. The diffusion is sometimes called inversion about the mean, which sounds abstract, yet it behaves like a steady push toward the marked component. The speed up is not because the machine checks all items and reports the match, like 1,000 clerks scanning a list. The speed up is because repeated interference amplifies one component of the vector. After about n iterations, the amplitude concentrates enough that measurement is likely to hit the target. Shor's algorithm is a deeper version of the same idea, and it carries historical weight because it changed what people feared. It creates a superposition over inputs, computes a periodic function coherently, then uses interference to reveal the period. The quantum Fourier transform is the lens, an operation that turns periodic structure into sharp peaks in the amplitude distribution. In both cases, the computation is not a classical branching tree, where each branch can be logged and inspected. It is a wave process where intermediate contributions are not individually observable, without destroying the effect. The computer is doing something, but it refuses to show its work in the way classical machines do. This is why superposition is not classical uncertainty, even when the math is used to predict probabilities. If it were, then learning which branch you were in would not change the future statistics. In classical probability, revealing hidden information updates your knowledge, but it does not physically erase alternatives. In quantum mechanics, learning which path destroys interference, because it forces the system to correlate with a record. The environment can learn it too, which is why the refrigerator is built like a fortress against information leakage. Even a faint thermal photon can carry away which path information, and the calculation unravels. Decoherence is not mystical collapse, and it is not a conscious observer reaching into the apparatus. It is entanglement with uncontrolled degrees of freedom, which turns phase relationships into inaccessible correlations. The phase is still there in the full universe, but it becomes unavailable to the subsystem we call the computer. Once phase information leaks, the amplitudes still exist in a larger state, but they stop interfering in the subsystem we can control. The computation becomes classically simulable noise, because the delicate cancellations are replaced by ordinary mixtures. In practice, the device begins to behave like a probabilistic classical machine with extra steps. So the lab fights for coherence because coherence is the resource that makes amplitudes meaningful, and because it is fragile in familiar ways. Coherence is what lets the vector behave like a single object. It is protected with shielding, filtering, careful materials, and timing that avoids unwanted resonances. On screen, the battle can be shown as a faint ripple trying to persist while static creeps in from the edges. A clean interference pattern slowly blurs into a uniform haze as phase information is lost. The visual metaphor is simple, but the physical message is exact. This is where the cosmological angle enters. If the state vector is too large to write down, what exactly is the machine manipulating when it runs? We can name the vector, and we can compute small cases, but for large the object becomes something we can only touch indirectly. One answer is operational and cautious, and it is the one engineers can live with. The vector is a predictive tool, and the device is a physical system whose statistics match that tool. If the predictions keep matching, we treat the model as adequate, even if we cannot print the full state on any storage medium. Another answer is ontological and unsettling, and it is the one that keeps philosophers awake. The vector is a real structure, and the device is steering something vast that exists whether or not we can represent it. In that view, the machine is not merely simulating a model, it is physically inhabiting the model's space of possibilities. Quantum computing forces this question because it turns the abstract into an engineered process, with knobs and calibrations and error budgets. We are no longer only predicting outcomes, we are programming the interference. The act of writing code becomes an act of shaping phases that no one can directly see. The exponential growth makes the programming feel like accessing hidden capacity, and that feeling is not entirely wrong. Each additional qubit is not one more switch, it is a doubling of the underlying description. The control problem scales too, because each qubit adds new ways to drift, couple, and leak information. This is also where Many Worlds enters the conversation, because it offers an intuitive story for the exponential bookkeeping. It says the branches are real and computation spans them. The story is seductive because it matches the numbers and because it turns an abstract vector into a narrative of diverging outcomes. In that story, the circuit creates a superposition of worlds that each carry a partial computation. Interference is then the mechanism that lets worlds combine their contributions. The wrong worlds cancel out, and the right worlds add up, leaving a single classical answer as a kind of residue. The many worlds picture is not required to do the math, and it does not change any experimental prediction. It is a way to interpret why the math seems to demand so much unseen structure. Some people find it clarifying, and others find it like replacing one mystery with a grander one. Skeptics reply that the vector lives in configuration space, not in a literal stack of parallel universes arranged like pages. They argue that the exponential is a feature of correlations, not extra worlds. In that view, the state is not many realities, but one reality with relationships too rich to compress. They point out that classical waves also interfere without invoking multiple realities, and that interference alone is not a metaphysical argument. The difference is that quantum amplitudes govern discrete outcomes and cannot be directly inspected. You can measure a classical waves field continuously, but you cannot read out a quantum amplitude without changing it. The dispute matters because of verification, and verification is where the romance meets the paperwork. If the computation outruns classical simulation, then our confidence rests on indirect checks and on the stability of interference signatures. We look for consistency across calibrations, for statistical fingerprints, and for behaviors that match theoretical constraints. But this chapter's point is narrower, and it is the foundation for everything that follows. Superposition is the minimal ingredient that creates the exponential state space, and interference is what turns that space into advantage. Without interference, the vector is just a large container, and size alone does not compute. Still, superposition alone does not explain the hardest part of quantum behavior, and it does not guarantee intractability. A large system can be in superposition, yet remain efficiently describable if it is separable. You can have many qubits each in their own small superposition, and the whole still factors neatly. If each qubit has its own independent state, the full state is a product, and the description scales linearly. The exponential only becomes unavoidable when the system is genuinely linked. The link is not a vague togetherness. It is a precise statement about what cannot be written as separate pieces. That link is entanglement. Entanglement is not an extra effect layered on top of superposition. It is what superposition becomes when applied to composite systems. It is the moment when the state of the whole contains information that no list of states of the parts can capture. In a product state, amplitudes factor into local pieces, and a classical computer can store those pieces compactly. In an entangled state, there is no set of local pieces that reproduces the whole. The correlations are not merely strong, they are structurally non-separable, and that is a different category of constraint. Entanglement makes the system a single non-classical object, even when the qubits are physically separated on a chip. It is the reason the 2 on amplitudes are not just redundant coordinates, but necessary degrees of freedom. The vector is not big because we are clumsy. It is big because the physics allows that much relational structure. So the suspense tightens in a specific way, and it tightens around a practical question. If we can build devices that sustain large-scale entanglement, then the exponential description is not optional bookkeeping. It is a physical demand enforced by interference patterns that refuse any simpler classical account. The machine behaves as if the full vector is being manipulated, even when no one can list its components. That is the unsettling bridge between engineering and metaphysics. We are stabilizing a structure we cannot fully represent, then asking it to return a classical string of bits. The output looks ordinary, yet the process that produced it may be beyond practical reconstruction. The result is a new kind of evidence, where the mechanism is inferred from constraints. We trust the computation the way we trust a distant star's composition, by the patterns it leaves in what we can measure. Superposition, properly understood, is not a mystical haze of possibilities that evaporates when we stare at it. It is a linear algebra that becomes real when phases collide and probabilities move. It is the grammar of quantum behavior, and interference is the sentence it speaks in public. And once many qubits share that algebra as one entangled object, the question stops being whether the computer works. The question becomes what kind of reality can host it. If the universe permits such states, then our everyday intuition is not wrong, but it is incomplete. Next, we follow the link that makes the state space truly inseparable, and we watch how correlations become a resource. We move from superposition as a vector to entanglement as a binding rule for the whole system. The refrigerator stays quiet, but the story becomes louder. Entanglement stops being a thought experiment the moment engineers have to budget for it, because the numbers refuse to stay philosophical. In the cold lab, it looked like a fragile correlation that noise could erase. In the open air, it becomes a signal that must survive distance, loss, and time. We start with the definition that refuses to stay intuitive, even when you say it slowly. An entangled state is a joint quantum state that cannot be factored into independent states. The whole contains information no list of local parts can reproduce, because the correlations are written into the combined description. In plain terms, you can know everything measurable about each piece, and still miss what the pair is doing together. Mathematically, the state vector or density matrix cannot be written as a simple tensor product. That failure to factor is not a technical detail. It is the feature that makes entanglement operational. This is what entanglement is not, and the negatives matter because the imagery misleads us. It is not a hidden wire carrying messages between particles. It is not a mystical sympathy that travels through space as a force. If it were a wire, we could tap it, amplify it, and route it like a radio link. If it were a force, it would come with a field and a speed. Instead, entanglement is a constraint on joint probabilities, and the constraint survives even when the outcomes look individually meaningless. Entanglement shows up as correlations that exceed classical bounds, yet still obey no signaling. Each side's outcomes look random when viewed alone, even when the apparatus is perfectly aligned. Only after comparing records do the patterns reveal the joint structure. The comparison step is crucial, and it is also where the drama hides. On each side, the detector clicks with no obvious message attached. Later, when timestamps are matched and measurement bases are revealed, the data lines up with a precision that classical models cannot cheaply imitate. Bell tests already told us the world will not be locally stitched together in the classical way. Chapter 2 tightened the logic until the classical escape routes looked contrived. Now the story changes scale, from meters to continents. Historically, that scaling did not happen overnight, and it did not happen by accident. Early Bell experiments fought detector inefficiencies and timing loopholes, because missing events can mimic weaker correlations. Over decades, optics improved, sources brightened, and synchronization became a science of its own. Distance matters because locality is a geometric claim, not just a philosophical preference. If two measurements are space-like separated, no light speed influence can coordinate them in time. The longer the baseline, the harder it becomes to hide coordination inside ordinary causal channels. Space-like separation is enforced with clocks, cables, and careful geometry, not with rhetoric. Engineers calculate light cones, then place settings, choices, and detections so that any signal would have to outrun light. The experiment is staged like a chase scene where the suspect never has time to arrive. Long baseline entanglement experiments begin as a practical extension of Bell logic, but they quickly become a test of systems engineering. Photons are created in pairs with linked polarizations or time bins. They are sent to distant stations through fiber or free space. The photon pairs often come from nonlinear crystals using spontaneous parametric down conversion, where one pump photon becomes two lower energy photons. The process is probabilistic, so the source must be bright enough to gather statistics. At the same time, it must be clean enough that multipair events do not wash out the correlations. The challenge is not only separation, the challenge is keeping the photons indistinguishable enough to preserve interference in the joint state. Loss, dispersion, and timing jitter all act like the environment listening in. Indistinguishability means the photons must match in spectrum, polarization, and arrival time within tight windows. A few picoseconds of drift can blur coincidence peaks, and a small polarization rotation can tilt the measured correlations. What looks like just noise is often a precise cumulative physics problem. Fiber networks push entanglement into the infrastructure of cities, where the path is stable but never perfectly quiet. Fibers add attenuation that grows exponentially with distance. Every additional kilometer is a tax on the probability that both photons arrive. At telecom wavelengths, the loss can be a fraction of a decibel per kilometer, which sounds small until it compounds. After tens or hundreds of kilometers, coincidence rates collapse, and the experiment spends most of its time waiting. The lab becomes a place of patience, with screens showing sparse clicks accumulating into meaning. Fibers also stretch and breathe with temperature, and that matters more than intuition expects. A warm afternoon can change optical path length enough to shift interference conditions. Stabilization systems respond like quiet custodians, constantly nudging phases back into alignment. Free space links trade fiber loss for atmospheric turbulence and pointing stability, and the visuals change immediately. The beam spreads, the air shimmers, and detectors fight background light. The experiment becomes a negotiation with weather and geometry. Through a telescope, the outgoing beam looks like a pale spear of coherence, but the atmosphere breaks it into wandering speckles. Adaptive optics and tracking motors chase the target in real time. Even city lights and moonlight become adversaries, raising the noise floor one stray photon at a time. In both cases, the correlations are not optional decoration. If the correlations drop below a threshold, the state becomes effectively classical. The entire point is to preserve a violation of classical bounds under realistic conditions. That threshold is not arbitrary, because Bell inequalities draw a line between what local hidden variable models can reproduce and what they cannot. When visibility falls, the violation shrinks, and the data can slip back into classical plausibility. The experiment is therefore a contest between entanglement and everything that imitates its loss. This is where the documentary's tension begins. A correlation that cannot be locally explained is now being routed, timed, and engineered. The question shifts from whether entanglement exists to how far it can be made to persist. The next milestone is entanglement distribution by satellite, where the laboratory ceiling is replaced by the night sky. Space-based links reduce absorption by lifting most of the path above the atmosphere. They also force the experiment to work while everything is moving. A satellite can act as a source that sends one photon to each of two ground stations. It can also act as a relay that receives and retransmits quantum states. Either way, the goal is the same: preserve entanglement across hundreds or thousands of kilometers. The moving platform adds constraints that are almost cinematic in their precision. The satellite races overhead, the line of sight opens and closes, and the link budget changes minute by minute. Ground stations swivel like searchlights, keeping the beams centered while the Earth turns beneath them. Space demonstrations proved that entanglement is not confined to tabletop optics. Photons can be entangled, separated by orbital distances, and still violate classical expectations. The sky becomes part of the apparatus. Visually, the apparatus is half observatory and half communications hub. Telescopes, cryogenic detectors, and racks of timing electronics. On monitors, coincidence histograms rise from noise like a faint constellation. Each successful run is not just a measurement, but an alignment of mechanics, optics, and probability. These tests also sharpen the locality story in a new way. The stations can be separated so widely that any subluminal coordination becomes implausible. Timing systems enforce that measurement choices and outcomes remain space-like, separated. This enforcement depends on more than fast electronics, because it depends on knowing when events occurred. Atomic clocks, GPS timing, and calibrated delays turn geography into a causal diagram. The experimenters are not merely collecting photons, they are defending a space-time arrangement. Yet the result remains the same kind of result we saw in the lab. Each station sees randomness that cannot be used to send a message. Only the joint statistics show the non-classical structure. That constraint is the key to why entanglement feels like a cosmic thread, but behaves like a disciplined resource. It is stronger than any classical correlation that respects local realism. It is weaker than a communication channel because it cannot carry controllable information by itself. The no signaling rule is not a patch to save relativity. It is built into the structure of quantum measurement. You can choose what to measure, but you cannot choose the outcome that appears. Even when the measurement basis is selected at the last moment, the click that follows is not a dial you can turn. Quantum theory gives probabilities, not commands, and entanglement does not change that bargain. The correlations emerge only when both parties later align their records, so entanglement cannot be used as a faster-than-light telegraph. If you try, you only generate local randomness. The universe gives you coordination without giving you control. Engineers learn to exploit exactly that combination, and this is where the tone shifts from mystery to utility. If correlations are strong but outcomes are unpredictable, then an eavesdropper cannot copy them without leaving a trace. This is where entanglement becomes security, not philosophy. Quantum key distribution can be done with prepare and measure schemes, but entanglement-based schemes make the logic explicit. Two parties share entangled pairs and measure them in chosen bases. They compare a subset to estimate how much correlation survived. The subset comparison is a kind of audit, and it is designed to be unforgiving. If noise or intrusion has weakened the correlations, the error rate rises and the Bell violation shrinks. The parties can then discard the run, or distill a shorter key whose secrecy is still defensible. If the observed correlations violate a Bell inequality under the right conditions, it implies a form of device-independent security. The security claim does not rely on trusting the internal details of the devices. It relies on the structure of the correlations themselves. This idea has a historical edge, because it treats the hardware as potentially adversarial. Instead of assuming detectors behave, the protocol asks the data to prove it. In that sense, Bell's inequality becomes not just a test of nature, but a test of trust. That structure is protected by a rule called monogamy of entanglement. Maximal entanglement between two systems limits how entangled either can be with a third. The correlations cannot be freely shared like classical copies. Monogamy matters because classical information can be duplicated without cost. A classical bit can be copied and forwarded while the original remains unchanged. Entanglement does not behave that way, even before we mention the no-cloning theorem. The no-cloning theorem adds a sharper edge to the same intuition. Unknown quantum states cannot be copied perfectly, because copying would require extracting information without disturbance. In entanglement-based protocols, that disturbance shows up as reduced correlation, which is exactly what the audit is watching. If an eavesdropper tries to share the same correlations, the shared state must change. The original pair becomes less entangled, and the statistics shift. The disturbance is not a technical flaw, it is the price of trying to distribute a correlation that is not locally owned. This is why entanglement is called a resource. It can be consumed, degraded, purified, swapped, and routed. It has a kind of accounting, and the accounting is enforced by physics. Resource accounting becomes literal in network design, where every link has a rate and every operation has a fidelity. You can spend entanglement to teleport a state, or you can save it for later swapping. The language sounds abstract, but the constraints show up as real throughput limits. Entanglement swapping shows how the resource can be extended without directly sending an entangled pair end-to-end. Two entangled pairs are created, and a joint measurement in the middle projects the outer particles into an entangled state. The endpoints become linked without ever interacting. The middle measurement is a Bell state measurement, and it is a strange kind of hinge. It does not reveal the endpoint's outcomes, yet it determines the relationship between them. In the visuals, it is a burst of optics and detectors that quietly rewires who is correlated with whom. In a network, swapping is the basic move behind quantum repeaters. Repeaters aim to beat the exponential loss of direct transmission. They do it by creating entanglement in shorter segments, storing it briefly, then connecting segments through swapping. But repeaters are not just classical amplifiers in disguise. Classical repeaters measure and resend, which copies information by destroying the original signal. Quantum repeaters must avoid measurement that would collapse the state into a classical record. So they require quantum memories that can store states without decohering. They require synchronization across nodes that may be separated by hundreds of kilometers. They require error handling that respects quantum constraints. Quantum memories are not generic storage, because they must preserve phase relationships as well as populations. Candidate platforms include trapped atoms, rare earth doped crystals, and other systems engineered for long coherence times. The memory must also interface with photons, because photons are the couriers of the network. This is where the engineering echoes the refrigerator. The environment is still the enemy, but now the environment includes fiber temperature drift, satellite motion, background photons, and clock instability. The same fragility scales into a systems problem. In the lab, you can close the door and stabilize the table. On a continent scale link, the table is the Earth itself, flexing and warming and vibrating. The experiment becomes a choreography of feedback loops, each one trying to keep the quantum description intact. Distance also forces a deeper question about what we mean by a quantum state. If the state is a bookkeeping tool, then the bookkeeping is now distributed across continents. If the state is a real physical structure, then that structure seems indifferent to space. Either way, the facts on the ground are stubborn. The joint statistics behave as if the pair is described together, even when the pieces are far apart. The state is not a little object travelling between stations. It is a rule for what can be jointly predicted. This is where the cosmological angle enters. Entanglement behaves as if spatial separation is not the fundamental barrier classical intuition expects. The correlations live in the joint state, and the joint state is not a thing located at a point. Quantum theory never says a wave function is a field in ordinary space. It lives in a configuration space that tracks possibilities for the whole system. When systems are entangled, that space cannot be decomposed into separate local stories. Configuration space is an awkward phrase, but the plain meaning is simple. To describe many particles, you need a space of combined possibilities, not a set of separate maps. Entanglement is the sign that the combined map contains features no single local map can carry. That fact invites a provocative framing. Maybe space is not the deepest substrate, but an emergent description built from more fundamental quantum relations. Entanglement then looks less like a signal across space, and more like a constraint that helps define space. We have to be careful here, because the documentary is not claiming a finished theory of quantum gravity. Ideas like holography and entanglement-based geometry are active research programs, not settled facts. Still, the direction of the hint is hard to ignore. In holographic dualities, information about a volume can be encoded on a boundary. In some proposals, patterns of entanglement help determine the connectivity of the emergent spacetime. The math is technical, but the narrative point is simple. Entanglement may be part of what makes where meaningful. It is worth pausing on the visual metaphor that researchers themselves sometimes use. If entanglement is reduced, the emergent geometry can look less connected, as though a bridge is thinning. The metaphor is not proof, but it is a disciplined way of asking what spacetime is made of. Even without quantum gravity, the operational lesson is already clear. Entanglement is measurable, and it can be distributed. It is not a metaphor for human connection. It is a physical correlation with strict limits and usable consequences. Those limits keep the story honest, and they also keep it interesting. No signaling prevents entanglement from becoming a causality loophole. Monogamy prevents it from becoming a freely shareable classical commodity. Decoherence prevents it from surviving without protection. So the universe offers a strange bargain. It allows correlations that violate local realism. It refuses to let those correlations become controllable faster than light influence. When entanglement is pushed across the sky, the experiment becomes a stress test of local realism under real-world constraints. Every kilometre reduces detection rates and increases opportunities for classical contamination. Yet the correlations persist when the system is engineered well enough. The phrase, engineered well enough, hides a brutal checklist: high-efficiency detectors, low-noise electronics, stable optics, and careful statistical analysis. It also hides the discipline of closing loopholes, because a weak link in the chain can reopen a classical explanation. The result must be clean, not merely impressive. That persistence is why the chapter calls entanglement a cosmic thread. It is not because it is mystical. It is because it behaves like a structural feature that does not thin out with distance the way classical causes do. Now we connect this back to the central question of the documentary. When a quantum computer produces results beyond practical classical verification, what is it exploiting? Is it merely using quantum mechanics inside one universe, or is computation distributed across parallel realities? Entanglement is the bridge between those options because it is the non-classical ingredient that scales. A product state can be simulated efficiently because it factors into local pieces. A highly entangled state resists that compression. This resistance has a technical face. The number of parameters needed to describe a generic entangled state grows exponentially with qubit count. Classical simulation can still work for special structures, but the general case becomes a memory and time explosion. The hardness is not mystical, it is combinatorial. Quantum processors are designed to generate, control, and protect entanglement on demand. 2-qubit gates create it, calibration maintains it, and error correction tries to stabilize it against noise. The philosophical puzzle becomes a control objective with a budget and a failure mode. On a chip, the visuals are smaller, but the stakes are similar. Microwave pulses or laser beams act like precise chisels, shaping interactions between qubits. The refrigerator returns as a quiet cathedral of metal, because thermal noise would otherwise flood the delicate correlations. In a network, entanglement is distributed between distant nodes. In a processor, entanglement is distributed between qubits on a chip. The geometry changes, but the logic is the same. The state of the whole cannot be reduced to local states of the parts. This is why verification becomes hard in the same breath that capability grows. If the device maintains large-scale entanglement, the classical description balloons. The output is a short bit string, but the process that produced it may be too large to reconstruct. So we are left with an uncomfortable modern question. How do you trust a machine whose internal state you cannot feasibly model? You can test fragments, sample outputs, and check consistency conditions. Yet the full wave function remains a kind of inaccessible ledger, too large to audit line by line. Many Worlds offers one story that matches the scaling. The computation is spread across branches, and interference recombines them to amplify consistent outcomes. In that story, entanglement is the bookkeeping that keeps branches correlated. Other interpretations keep one world and accept non-local structure, contextuality, or a wave function that is not a physical object in space. They argue that entanglement is about constraints on joint probabilities, not literal parallel histories. The experiments do not choose between these stories, but the engineering does something the old debates could not. It takes entanglement out of the realm of rare demonstrations and turns it into a repeatable operation. It makes the question harder to dismiss as philosophical taste, because once entanglement is a resource, the universe is no longer merely described by quantum theory. The universe is being programmed through quantum theory. The same correlations that violated Bell inequalities are now being scheduled, routed, and protected. That is the unsettling shift in this middle chapter. We're not only observing that reality is non-classical, we are learning to industrialize the non-classical part. The chapter ends where the next escalation begins. A satellite link proves entanglement can span the sky. A quantum processor tries to make entanglement span a computation. If entanglement is a cosmic thread, then a quantum computer is a loom. It weaves joint states that classical physics cannot locally account for. It then asks those states to return an answer we can read. Next, we follow what happens when that loom grows large enough that classical auditing breaks down. We move from distributing entanglement across space to distributing it across complexity. The question stops being whether the thread exists and becomes what it is stitching together. The outputs still look like ordinary bit strings and histograms, even as the internal state becomes unwritable to any classical notebook. That mismatch keeps pulling us back to the same wound in quantum theory. What exactly happens when a quantum possibility becomes a single recorded fact? Quantum mechanics gives two stories that do not easily fit together, and the tension is not subtle once you listen for it. Between measurements, the wave function evolves smoothly by the Schrödinger equation, rotating through Hilbert space like a perfectly reversible clockwork. At measurement, the textbook inserts collapse, and the state jumps to one outcome as if the other alternatives were never there. This is the measurement problem in its blunt form, and it survives every attempt to rephrase it politely. The mathematics says unitary evolution is universal and reversible, which means information is never truly destroyed in the global description. The narrative says measurement is special, irreversible, and exempt from the unitary rule, an exception that arrives exactly when we ask the theory to meet experience. The problem is not only philosophical discomfort, and it is not merely a debate about words. The problem is that quantum theory never clearly defines what counts as a measurement, even though measurement is where the theory touches the world we report. If collapse is real, we need a boundary between quantum system and classical apparatus, and we need that boundary to be stated in physical terms. That boundary is hard to locate in the lab because the lab is not divided into neat conceptual boxes. A qubit couples to a resonator, then to an amplifier, then to room temperature electronics, and finally to software that prints a number. At which step does the wave function stop evolving unitarily and start collapsing, and what physical parameter marks the change? In practice, engineers treat measurement as a physical interaction that creates a stable record, and that definition is brutally operational. The record is a macroscopic correlation that cannot be undone with available control because too many degrees of freedom have been dragged into the correlation. Yet the underlying equations still describe everything, including the apparatus, as quantum, which makes the word measurement feel like a label we paste onto ignorance. Decoherence explains why the record looks irreversible, and it does so with real mathematics rather than hand-waving. The system entangles with uncontrolled degrees of freedom, and phase information becomes inaccessible to the limited subsystem we can isolate. interference between alternatives becomes effectively impossible for the reduced state we can manipulate, because the environment has carried away the relative phases like heat diffusing into a room. Visually, decoherence is not a mystical flash, but a spreading stain. The clean interference fringes blur, the off-diagonal terms in the density matrix shrink, and the state becomes locally indistinguishable from a classical mixture. The world looks as if it has chosen, even though the global wave function, if you keep it, has only become more entangled. Decoherence is powerful, but it does not finish the story, and that gap is where the unease hides. It turns a pure superposition into an apparent mixture for local observers, which is exactly what we need to explain why macroscopic objects look definite. It does not select one definite outcome from the mixture, and it never tells us why one record is experienced rather than all records existing quietly in parallel. So collapse remains as an extra postulate in many standard tellings, a rule that arrives when the rest of the theory runs out of vocabulary. It is added to connect the unitary math to the single outcome we experience, and it works operationally with astonishing accuracy. But it leaves the boundary undefined, and it leaves the mechanism undescribed, which is a strange place for a fundamental law to hide. This is where the documentary's tension begins. If we cannot define measurement cleanly, then we cannot say when the world becomes one story, rather than many competing stories in superposition, and quantum computers are built to delay that moment as long as possible, because their power lives in the time before the record hardens. A quantum processor is engineered to keep evolution unitary across many gates, even while it sits inside a noisy, imperfect universe. It tries to prevent the environment from learning which path the computation took, because which path information is poison to interference. The refrigerator, shielding, attenuators, and filters are all attempts to postpone effective measurement, and to keep the qubits from leaking their secrets into stray modes. The goal is not mystical, and it is not a claim that the machine is thinking in a supernatural way. The goal is to preserve interference long enough to shape probabilities at the end, so that amplitudes add or cancel with surgical precision. The device behaves as if many alternatives remain present until readout, because the algorithm depends on that controlled ambiguity. But if collapse is a physical event, the processor is skating near it, and the ice is thin. Every stray photon and every defect is a potential measurement, because each can carry away information that distinguishes alternatives. Every uncontrolled coupling is a potential collapse trigger, and the engineering challenge becomes a quiet war against the universe's tendency to eavesdrop. Textbook collapse makes the story feel safe, because it keeps reality single by decree. It says the wave function is only a tool for prediction, not a literal structure that must be taken seriously. It says reality stays one, and the math merely updates when information appears, like a ledger corrected after a transaction. Yet collapse also feels like an admission of ignorance, and the feeling is hard to shake once you notice it. It says the most important step in the process is not described by the same rules as everything else. It says the universe needs two kinds of time evolution, and it never tells us what physical switch flips between them. In 1957, Hugh Everett proposed the simplest escape, and simplest here means something almost brutal. Remove collapse entirely and keep unitary evolution universal, with no exceptions and no special moments. Let the wave function describe everything, including observers and measuring devices, even if that forces us to rethink what an outcome means. Everett's many worlds interpretation begins with a refusal, and that refusal is the core of its appeal. It refuses to add a special measurement postulate, and it refuses to declare a classical realm that sits outside quantum law. Historically, it arrived in a climate shaped by Bohr's caution and von Neumann's formalism, and it sounded to many like an act of rebellion disguised as mathematics. In many worlds, measurement is just entanglement, and the word just is doing heavy work. The system becomes correlated with the apparatus, and the apparatus becomes correlated with the observer, and the correlations propagate outward. The combined state evolves into a superposition of consistent records, each record internally coherent and each record carrying its own version of what happened. Each record corresponds to an outcome we would call definite, because within that record everything agrees. The observer in one branch sees one result and not the others, and their memory locks onto that history. The other results exist in other branches, no longer able to interfere because the correlations have spread too widely to be recombined. Decoherence is the mechanism that makes branches effectively separate, and it gives the story its physical bite. Environmental entanglement spreads phase information into degrees of freedom we cannot track, Like phonons in a chip or photons in a cable, the branches become dynamically isolated, even if the global state remains pure, because reversing the entanglement would require impossible control over the environment. Branching is not a dramatic explosion of new universes in space, and it is not a science fiction portal opening in the lab. It is a change in the structure of the universal wave function, a reorganization into components that stop interfering. It is the growth of non-interfering components that each contain a stable record, and the stability is what makes them feel like separate classical worlds. Many Worlds claims it avoids the measurement boundary problem, because it never needs to draw a line. There is no moment when quantum rules stop and classical rules begin, and no privileged place where the equations must be suspended. There is only unitary evolution plus decoherence that explains why outcomes look classical locally, even though the deeper description never collapses. Many Worlds also avoids the need for a collapse trigger, which is where many alternative stories get stuck. No one has to decide whether a detector, a neuron, or a conscious mind counts as measurement, because the dynamics does not depend on that choice. The same rule applies at every scale, from an ion trap to a galaxy, and that universality is part of its seduction. But the price is heavy, and it is paid in ontology rather than equations. The theory keeps every outcome that the wave function assigns non-zero amplitude, and it refuses to throw any of them away. Reality becomes a constantly branching structure of effectively separate histories, and the word effectively is the thin membrane between physics and vertigo. This is why Many Worlds feels terrifying, even to people comfortable with quantum math and indifferent to metaphysical drama. It does not merely say the future is uncertain before measurement, which is already unsettling. It says the future contains all the outcomes each realized, and our experience is a local thread through a much larger tapestry. The terror is not only cosmic, and it is not limited to abstract talk about the universe. It is personal and immediate because it touches the continuity of the self. If branching is real, then personal identity becomes a pattern that splits into multiple continuations, each one sincerely believing it is the original. The question becomes hard to phrase without sounding like fiction, which is part of why it is often avoided. Which future is you if every outcome contains a version of you, each with the same memories up to the split? What does it mean to anticipate one experience when the theory predicts many, and when anticipation itself becomes something like a distribution? Many Worlds answers with a kind of disciplined humility, and it tries to keep the language sober. Each branch contains an observer who remembers a consistent past, and those memories are what make the branch feel like a world. Each observer experiences a single outcome and calls it reality, because from inside a branch there is no access to the others. Probability becomes a new kind of problem, and it is not a minor technicality. If all outcomes occur, what does it mean to assign chances, and what does it mean to be surprised? Why should squared amplitudes, the Born rule, govern what we expect, if expectation is not about which outcome exists, but about which outcome we will find ourselves reporting? Everett's followers argue that the Born rule can be derived from rational decision theory or symmetry arguments, and the literature is dense for a reason. Critics argue those derivations smuggle in assumptions about probability and typicality, and that the conclusion is not as clean as advertised. The debate remains active and technical, and it is one of the places where philosophy and physics genuinely overlap. Still, Many Worlds is not a free-for-all, and it does not license arbitrary miracles. It does not allow outcomes that violate quantum statistics, and it does not change the interference patterns we measure in the lab. It keeps the same equations and the same experimental predictions as standard quantum mechanics, which is why it can hide in plain sight. That equivalence is both its strength and its weakness, and the documentary has to sit with that discomfort. It means Many Worlds is hard to falsify by ordinary experiments because it agrees with the numbers. It also means it can be dismissed as philosophy because it changes no numbers, even while it changes what the numbers are said to describe. Yet the interpretation keeps resurfacing, especially around quantum computation, where the abstract becomes engineered hardware. It returns because the state space grows exponentially, and because interference seems to require unseen structure that cannot be pictured classically. The metaphor of branching worlds feels like it matches the bookkeeping, and the bookkeeping is no longer a chalkboard game. Here we have to be careful with language because metaphors can harden into claims without anyone noticing. A quantum computer does not output to and answers we can read, and no laboratory has a printer that spits out parallel universes. It evolves one state vector through unitary gates, then samples one outcome at measurement, and the sampling is the only part we directly observe. But the internal evolution can be described as a superposition over many computational paths, and that description is not merely poetic. Different paths accumulate different phases, and phase is the currency of interference. The algorithm engineers those phases so that paths cancel or reinforce, and the final distribution is sculpted rather than searched. This is where the popular claim appears, and it spreads because it feels like an explanation rather than a formalism. Quantum computers compute in parallel universes, then interfere to select the right answer, and the phrase sticks in the mind. It is a vivid story, and it is not entirely empty, because it gestures at the real structure of superposition and recombination. In a many-worlds framing, each branch carries a component of the computation, like a set of partially separated narratives evolving under the same unitary rule. The branches are not independent classical threads, because they can still interfere before decoherence isolates them. The final measurement correlates the observer with one branch's output, and the other outputs remain as inaccessible records in other branches. In that story, the exponential speed-ups feel less like magic and more like accounting. The machine is not doing an impossible amount of work in one world, and it is not cheating by hiding complexity. It is distributing amplitude across a vast set of branches, then recombining them, and the recombination is where the advantage actually lives. But we must mark the boundary between metaphor and claim, because the boundary matters for evidence. Many worlds is an interpretation of the same unitary math used by every quantum engineer, regardless of their philosophy. The algorithms do not require believing in literal parallel universes, and a working device does not come with an ontological label attached. A Copenhagen-style instrumentalist can tell the same computational story, with a different emotional temperature. The wave function is a tool that encodes probabilities for outcomes, and it is not required to be physically real. The unitary evolution is a rule for updating the tool between measurements, and collapse is an update when a result is registered. A Bohmian can tell another story, and it is strangely classical in its imagery. Particles have definite positions guided by a pilot wave in configuration space, and the guidance equation does the hidden work. The wave never collapses, but the world remains single in the sense of one actual configuration, and the other possibilities are empty waves. A collapse theory advocate can tell yet another story, and it tries to pay the price in new dynamics. The wave function really collapses, but collapse is a physical process with a rate or mass dependence, and it can be written into modified equations. The quantum computer works because collapse is rare at the scale of qubits, yet it becomes significant for macroscopic records. All of these stories can agree on the same circuit predictions, which is the uncomfortable fact that keeps interpretation debates unresolved. The machine's success does not automatically pick a metaphysics, and it does not tell us what the wave function is. It tells us that the formalism works, and that we can engineer it, which is both impressive and evasive. Still, quantum computing changes the emotional weight of the question, because it turns interpretation into a design constraint. It takes the measurement problem out of a lecture hall and puts it into a device that must be tuned, shielded, and calibrated. It makes the boundary between unitary evolution and classical record a design parameter, measured in coherence times and error rates. When a processor scales, it forces a practical version of Everett's question, and it does so with financial and experimental pressure. If the wave function is only a tool, why does the tool require an exponentially large description, even when we cannot store it anywhere? If the wave function is real, what is the device physically steering when it steers phases through an invisible space? This is where the cosmological angle enters, and the camera can pull back without changing the subject. Many Worlds says the universal wave function is the fundamental object, and everything else is emergent structure inside it. Branching is not an add-on, but the normal consequence of quantum interactions at every scale, from microscopic scattering to the growth of galaxies. On that view, the early universe was not one classical history waiting to be revealed by later measurements. It was a quantum state that decohered into many quasi-classical histories, each with its own pattern of density fluctuations and its own arrow of time. Our cosmological story becomes one branch among countless alternatives, and the night sky becomes a local archive rather than a global verdict. That shift is not just about science fiction multiverses, and it is not merely a way to make the universe sound bigger. It is about what we mean by a single past, and why the past feels fixed. If branching is real, then the past we remember is one consistent record inside a larger superposition, stabilized by decoherence and reinforced by every redundant copy of information in the environment. The unsettling part is that nothing in the equations privileges our branch, and nothing marks it as the real one. The branch feels special because it contains our memories and our data, and because our instruments are part of its record. Manyworld says that feeling is a local fact, not a global selection, and that is a hard sentence to live with. Critics push back with a different discomfort, and it is not simply emotional resistance. They argue that Manyworlds reifies a mathematical object without necessity, turning a calculational device into a literal universe. They say the wave function lives in configuration space, not in ordinary three-dimensional space, which makes worlds sound like a metaphor stretched too far. They argue that calling components of the wave function separate worlds is a category mistake, because the components are terms in a high-dimensional description of correlations. The exponential growth reflects relational complexity, not a literal multiplication of universes, and the language of branching can mislead. The critique is that we are mistaking our representation for the represented. They also point out that classical waves can interfere without implying multiple realities, and interference alone is not evidence of branching worlds. Quantum theory is stranger because outcomes are discrete, and because measurement produces records we treat as facts. But the math still describes one evolving state, and the question is what we are entitled to say that state means. Manyworlds supporters answer that the universal state is the simplest ontology that matches the equations, and that simplicity has a particular flavour. If you take the unitary evolution seriously, you get branching as a consequence, because entanglement does not politely stop at the edge of the apparatus. Collapse then looks like the extra assumption, not many worlds, and the burden of explanation shifts. So the dispute becomes a trade, and neither side gets everything it wants. Keep one world and add a special collapse rule, or keep one rule and accept many branches, each as real as the others. Either way, something that feels obvious must be surrendered, and the surrender is what makes the debate endure. Quantum computing sharpens that trade because it weaponizes coherence, turning a fragile quantum feature into a technological resource. The device is built to maintain superpositions that would decohere in ordinary conditions, and it does so by isolating, cooling, and correcting. It is built to keep alternatives alive long enough to interfere, and then to convert that interference into a classical readout. In a collapse story, the processor is a delicate system that must avoid triggering collapse too early, and the threat is ever present. In a many-world story, the processor is a controlled branching and recombination process inside the universal wave function, and the engineering challenge is to prevent uncontrolled branching into the environment. The same hardware supports both narratives, which is part of the mystery. The two stories predict the same output distribution for ordinary circuits, and that agreement is the reason the argument cannot be settled by a simple benchmark, but they suggest different intuitions about what the machine is doing while it runs, and intuitions matter when evidence becomes indirect. One says the wave function is bookkeeping, the other says it is the machinery, and the difference is not trivial once we stop being able to check the bookkeeping. This matters because of verification, which earlier chapters set up as the coming crisis, and now the crisis has teeth. When the computation outruns practical classical simulation, we cannot reconstruct the full state, even in principle with our available resources. We can only test indirect signatures and consistency constraints, and we have to trust that those signatures track the right underlying structure. If verification is indirect, then interpretation becomes harder to quarantine, because the story starts to lean on what cannot be seen. People start asking what the indirect evidence is evidence of, and what exactly is being confirmed. Are we confirming a model of probabilities, or confirming a picture of reality? And does the difference matter once the state is too large to write down? The many-worlds framing gains rhetorical power here, and it gains it for understandable reasons. If the state space is too large to store classically, it is tempting to say the computation is happening across many worlds, because that sounds like a physical home for the exponential. It feels like an explanation for where the complexity goes, even if the formalism never required that language. But rhetorical power is not proof, and the documentary has to keep that distinction sharp. The same exponential appears in any interpretation that keeps the standard Hilbert space formalism, because the formalism itself carries the growth. The hard part is not the story, but the structure of entanglement and interference, and the way those structures constrain what any observer can extract. So we keep the claim in its proper box, even as we admit why the box keeps leaking. Quantum computers have not proven many worlds, and they have not forced a verdict on collapse. They have proven that large-scale unitary evolution can be engineered, stabilized, and exploited before measurement, and that achievement alone reopens old questions with new urgency. Still, the box keeps leaking, because many worlds removes the one step that feels like a cheat, and it does so without changing the equations. It replaces collapse with branching, and branching with decoherence, and decoherence with ordinary unitary physics. That chain of replacements is what makes the hypothesis unsettling, because it makes the weirdness feel like a direct consequence of the rules. If it is right, then measurement is not a moment when reality chooses, and it is not a cosmic coin flip that selects one outcome. Measurement is a moment when reality divides into records that cannot meet again, because the information needed to reunite them has been smeared into the environment. The choice is not made by the universe, but by our location inside one decohered record. And the quantum computer becomes a small, repeatable version of that division, carried out on a benchtop under fluorescent lights. It creates a superposition of computational histories, then recombines them to sculpt an answer, and the sculpting is visible only in statistics. It ends by producing a classical record that locks one branch into place, and the lock is made of amplification, redundancy, and irreversible correlations. The central question now becomes sharper, because the engineering success forces us to say what we think is happening. When a quantum computer produces results beyond practical classical verification, is it merely exploiting quantum mechanics inside one universe? Or is it evidence that computation is distributed across parallel realities, as many worlds suggests, even if those realities cannot communicate after decoherence? We cannot answer that by rhetoric, and we cannot answer it by comfort, because both are cheap. We need to ask what kind of evidence could ever distinguish interpretations, given that they share predictions in ordinary regimes. We need to ask whether verification methods accidentally privilege one story, and whether our tests are sensitive to ontology or only to statistics. This is the transition to evidence. If many worlds is just philosophy, why does it keep resurfacing in discussions of quantum breakthroughs and verification, even among cautious researchers? Why does the engineering language keep drifting toward branching, interference, and inaccessible global states, as if the hardware is forcing metaphors into our mouths? Next, we follow the verification crisis to its edge, where confidence becomes a matter of structure rather than full reconstruction. We examine how researchers test machines they cannot fully simulate and what those tests actually certify. We ask whether those tests are only practical, or whether they quietly constrain what one world can mean. In rooms colder than deep space, the machines return bit strings that look ordinary, almost boring, as if nothing exotic happened at all. Frosted vacuum cans sit under braided cables and microwave lines, while control racks blink in steady, indifferent rhythms. Yet inside those metal cylinders, at millikelvin temperatures, superconducting circuits behave less like wires and more like quantized resonators. The unsettling question is not whether quantum computers work. The question is what kind of reality they must be using when ordinary digits arrive from an extraordinary interior. Chapter 5 left us with a fork that refuses to close, and the fork is not merely philosophical. Either the wave function is bookkeeping that updates at measurement, a compact summary of what we can predict, or the wave function is the machinery, evolving unitarily without collapse, with outcomes as decohered branches that no longer interfere. Both stories reproduce the same lab statistics, and that is precisely the problem. If interpretations agree on every number, what would ever force us to choose? Now the story becomes experimental again, and the stakes become public, because the numbers start to outrun our usual auditing tools. Quantum processors start crossing a line called quantum advantage, and that line is drawn in runtimes and resources, not in metaphors. The line is not metaphysical, but it pressures every metaphysical story, because it changes who can check what. When the experiment becomes too large to mirror on a classical machine, the lab itself begins to feel like a boundary. Quantum advantage means a specific comparison, not a vague sense of progress or a marketing slogan. A quantum device performs a task faster or with fewer resources than the best-known classical methods under comparable assumptions. The claim is always conditional on what we count as the task, and on what counts as fair cost. Are we comparing wall clock time, energy, memory, or total hardware? Are we allowing massive parallelism or only a single classical node? The task is often not factoring or chemistry, at least not yet, because today's devices are still noisy and relatively shallow. The task is sampling from a distribution defined by a quantum circuit, where the circuit itself is the specification. The output is a histogram over many bit strings, not a single certified answer that can be checked with a calculator. That choice is not arbitrary. Sampling is what these machines naturally do when you measure qubits at the end of a circuit. This is where the documentary's tension begins. Science depends on verification, yet quantum computing pushes us toward regimes where verification becomes statistical, indirect, and assumption-laden. We are used to experiments where a theory predicts a number, and we compute that number to compare. Here, the theory predicts a distribution, and computing that distribution is the thing we cannot afford. Researchers choose sampling tasks because they are native to quantum hardware, and because they amplify the difference between quantum state space and classical representation. A random circuit scrambles amplitudes across an exponential space, distributing complex phases so that interference becomes both intricate and fragile. The resulting distribution is believed hard to reproduce classically, even if each sample is easy to print. One bit string is cheap. The pattern of which bit strings appear, and how often, is where the cost hides. Random circuit sampling is simple to state and brutal to simulate, which is why it became a benchmark in the first place. Start with all qubits in a known state, often the all-zero computational basis state. Apply layers of random single qubit rotations and entangling gates, then measure in the computational basis at the end. On a chip, those layers are microwave pulses and tuned couplers, timed to nanoseconds, fighting drift and crosstalk. On a classical computer, those same layers imply tracking a vector with two uncomplex amplitudes. Each run produces one bit string, and the machine can repeat runs quickly, sometimes millions of shots in a short session. The claim of advantage is about generating many samples from that distribution, not about discovering a hidden message. The classical challenger must approximate the same distribution within a defined tolerance, typically expressed in total variation distance or a related metric. That tolerance matters, because noise already moves the target away from the ideal circuit. The hardness argument is not a proof in the everyday sense, and it is not a theorem that says forever, no classical algorithm can compete. It is a web of complexity assumptions tied to counting problems, and those assumptions have survived decades of scrutiny. If a classical computer could efficiently sample these outputs, then widely believed conjectures in complexity theory would fail, and entire hierarchies of problems would collapse in unexpected ways. The argument is conditional, but it is not casual. The intuition behind the hardness is about interference and cancellation, which is easy to say and hard to feel. The probability of one output depends on a sum over exponentially many paths through the circuit, where each path contributes a complex amplitude. Those amplitudes add like waves, sometimes reinforcing and sometimes annihilating, so the final probability can hinge on delicate phase relationships. Estimating those probabilities resembles computing a partition function in statistical physics, or a permanent-like quantity in combinatorics, where small errors can be fatal. But the documentary cannot let the word hard do all the work, because hardness has technical caveats that matter in the lab. Hardness is often about worst-case instances, while experiments produce noisy average-case data drawn from a random ensemble. So the argument must be tightened into something testable, and that tightening is where debates flare. What does it mean to be hard on average, when the device itself is imperfect? Researchers rely on average-case hardness conjectures for random circuits, because random instances are what the hardware can generate without hidden structure. They also rely on anti-concentration, meaning probabilities spread out rather than collapsing into a few outcomes. Anti-concentration makes the distribution spiky in a typical way, with many outputs having small probabilities and a few being noticeably heavier. Together, these claims suggest that approximating the distribution is classically intractable, even if no single output is special. Yet the output of the quantum device is not the distribution itself. It is a finite sample from the distribution, contaminated by noise that accumulates gate by gate, qubit by qubit. Relaxation and dephasing erase phase information, while control errors tilt rotations away from their intended angles. verification becomes a question of whether the sample has the right fingerprints, not whether it matches an unreachable ideal perfectly. The fingerprint is statistical, and it must survive the machine's own imperfections. This is where the word supremacy appeared, and why it became controversial beyond the technical community. It sounded like a declaration of final victory over classical computing, and it carried historical baggage that had nothing to do with circuits. In practice, it means a narrow benchmark, with caveats, and with a moving classical target. The more careful phrase, quantum advantage, points to a specific gap on a specific task at a specific time. A quantum advantage experiment is therefore a three-part claim, and each part can be attacked separately. The device implements a specified circuit family at a given size, with a documented layout and gate set. It produces samples consistent with that family's ideal distribution, up to a quantified noise model. No known classical method can match the sampling at comparable cost, given the same tolerance and the same definition of resources. The third part is always provisional, because known can change. The second part is the verification bottleneck, and it is where the narrative becomes almost forensic. For small circuits, we can compute the ideal probabilities exactly, and we can compare shot-by-shot statistics to a trusted simulation. For large circuits, exact computation becomes infeasible, so the experiment must validate without full simulation. That shift is subtle in wording and enormous in consequence. Cross-entropy benchmarking is one of the standard tools, and it is built to extract signal from limited classical access. For a set of measured bit strings, compute their ideal probabilities for a circuit size that is still classically simulable, often by restricting qubit count or depth. Compare the observed sample to what the ideal distribution would favour, and ask whether the machine is correlated with the ideal. The method does not reconstruct the state. It checks whether the device tends to land on higher probability strings more often than chance. The score is a proxy for fidelity, not a direct proof of quantum speedup, and it can be misunderstood if treated like a certificate. It asks whether the device outputs strings that are more likely under the ideal distribution than random guessing would be. It turns verification into a statistical correlation test, where the null hypothesis is uniform noise. In visuals, it looks like two histograms sliding past each other, searching for alignment in their peaks. Heavy output generation is another related idea, and it has an appealing simplicity when spoken aloud. For a given circuit, label outputs as heavy if their ideal probabilities exceed the median of the ideal distribution. A correct quantum device should produce heavy outputs more often than a uniform sampler, because it is biased toward the same, heavier regions. The test reduces a complicated distribution to a yes or no label per sample, which makes it robust in some settings. It also hides detail, which is both its strength and its weakness. These tests are clever, but they are also fragile in ways that matter when the goal is public confidence. They require computing ideal probabilities for the tested circuits, and that computation is exactly what becomes impossible at scale. That limits them to smaller instances, or to subsets of outputs, or to approximate classical calculations. The moment you rely on approximations, you inherit their assumptions, and the chain of trust lengthens. So the experimenters build a ladder of trust rung by rung, and each rung is documented like a calibration ritual. They validate gate errors on small subsystems, measuring single qubit and 2-qubit fidelities, leakage rates, and crosstalk patterns. They validate smaller circuits end-to-end where classical simulation is possible, checking that metrics scale as expected with depth. Then they extrapolate that the same physical model holds at larger sizes, where direct comparison is no longer available. The ladder is not perfect, but it is the only way forward. This ladder is not unique to quantum computing, but the gap is new in its severity. In most sciences, the model predicts the data and can be computed, even if the computation is expensive. Here the model predicts the data, yet computing the prediction is the hard part, and that flips the usual direction of explanation. The device becomes the only practical calculator for its own distribution. We are left comparing shadows to shadows. The verification dilemma has a sharp version that cannot be dodged, and it sits like a cold stone in the middle of the field. If the quantum device is truly beyond classical simulation, then classical checking is also beyond reach. Verification must become indirect, or it stops. That is not a failure of scientific rigor. It is a recognition that rigor can take different forms when the object is computationally vast. Indirect verification means we test necessary conditions, not full equivalence, and we do it in multiple overlapping ways. We check that marginal distributions match expectations, such as single qubit measurement biases and pairwise correlations. We check that error rates scale in the right way as depth increases, rather than jumping unpredictably. We check that the output is not trivially compressible, because compressibility can signal hidden structure. Each check is incomplete, but together they constrain the space of plausible explanations. We also check for signatures of known classical spoofing strategies, because the benchmark itself can be gamed. A classical algorithm might exploit structure, noise, or limited depth, and it might match the benchmark metric without matching the intended distribution. It might learn a simplified model that reproduces heavy output rates while missing higher order correlations. It might exploit the fact that the device's noise pushes outputs toward uniformity, where many metrics lose sensitivity. In this context, the adversary is not malicious, the adversary is ingenuity. This is why random circuits are designed to be structureless, or at least to look structureless to algorithms that hunt for patterns. The randomness aims to remove exploitable symmetries and to prevent shortcuts based on periodicity or low entanglement. The circuit depth is tuned to generate high entanglement and chaotic-like behavior, while staying within coherence limits that are measured in microseconds. Visually, the chip's connectivity graph becomes a battlefield map, with entangling gates marching across it in layers. But noise creates structure of its own, and that is a recurring theme that refuses to stay in the background. Depolarizing noise pushes the distribution toward uniformity, flattening the spikes that anti-concentration predicts. Coherent errors can create bias patterns that a clever classical model might imitate, because systematic miscalibrations repeat across shots. Even measurement errors can imprint recognizable signatures, like an accent that betrays the speaker. The experiment is not only about quantum mechanics, it is about controlling imperfections well enough that quantum mechanics still dominates. So verification becomes a contest between two explanations, and the contest is fought with statistics rather than with direct reconstruction. One explanation is that the device is sampling from a hard quantum distribution with some noise, as the hardware model predicts. The other explanation is that the device is sampling from an easier distribution that still passes the chosen tests. The more indirect the tests, the more carefully they must be designed to rule out imposters. The drama is not just in the machine, it is in the logic of the check. This is where the documentary's tension begins again, in a more uncomfortable form because the uncertainty is structural. When the tests are statistical and partial, confidence becomes a matter of inference, not a matter of direct comparison. The inference depends on assumptions about what classical computers cannot do, and on what kinds of approximations are unlikely to succeed. Those assumptions are informed by evidence, but they are not the same as a measurement. The audience is asked to accept a new kind of scientific argument, one that blends lab data with complexity theory. Complexity theory enters as a kind of invisible witness, and it speaks in conditional statements that sound like riddles. It does not tell us what the device did. It tells us what would follow if a classical device could do the same thing efficiently, under standard definitions of efficiency. The witness is persuasive because it connects the experiment to a broader landscape of computational difficulty. But it is also frustrating because it never says, therefore, the quantum device must be doing X. It says, if not, then something deep would break. The argument often uses reductions to counting problems, which are notorious because counting is harder than deciding. Approximating output probabilities relates to estimating amplitudes, which relates to notch p-hard quantities that sit beyond NP in the usual hierarchy. The leap from exact hardness to approximate sampling is where the controversy lives, because experiments never produce exact distributions. Real devices drift, and real verifiers tolerate error. The question becomes whether approximate sampling still forces classical algorithms into the same hard corner. Researchers try to close that gap with additional conjectures, and they do it with care, because conjectures are not thrown around lightly in this community. They assume that approximating these probabilities on average remains hard, not just for contrived worst cases. They assume that small total variation distance still requires solving hard subproblems, rather than skirting them with clever smoothing. These are not arbitrary beliefs, but they are beliefs supported by decades of complexity evidence, and by the stubborn absence of classical breakthroughs. Still, they are not the same as a direct experimental check, and that distinction matters. So we enter an era where a quantum experiment can outpace classical reproducibility, and the asymmetry is not just about speed. The device can generate data faster than we can compute what the data should look like. even with supercomputers and optimized code. That is a new kind of scientific asymmetry, and it changes the emotional texture of the lab. The machine becomes a producer of patterns that we can sample but not fully predict. We can interrogate it, but we cannot exhaust it. The asymmetry reshapes what it means to claim a discovery, because discovery has always implied some form of independent check. In particle physics, we can simulate backgrounds and detector responses, and we can rerun the analysis with different assumptions. In quantum advantage, the background is the best classical algorithm, and it keeps improving as soon as a benchmark is announced. The classical world is not passive. It reacts, adapts, and sometimes surprises. This is why quantum advantage claims are time-stamped. Like photographs of a moving race, a device is faster than the best-known classical method at the time, given the best available hardware and the best published techniques. A later classical algorithm can narrow the gap, or even erase it for that benchmark without changing the quantum device at all. That does not negate the experiment. It reveals how tightly the claim is tied to a shifting frontier. The point is not that quantum advantage is fake, and it is not that the goalposts are dishonest. The point is that it is a moving frontier between two toolchains, each with its own strengths and its own forms of creativity. One toolchain is physical hardware exploiting interference, entanglement, and the geometry of Hilbert space. The other toolchain is classical ingenuity exploiting approximations, sparsity, tensor decompositions, and whatever structure noise accidentally provides. The frontier is where both sides learn. This frontier creates a new kind of skepticism that is rational, not hostile, and it is healthy when it stays precise. If you cannot verify the claim distribution directly, you ask what else could produce the same metrics. You ask whether the benchmark rewards the intended quantum behavior, or whether it rewards a particular pattern of errors. You ask whether the verification method is sensitive to the difference between quantum chaos and classical mimicry. In a mature science, skepticism is a tool, not a weapon. The community answers with layered evidence, and the layers are meant to be mutually reinforcing rather than mutually dependent. They publish calibration data, error models, and scaling curves, showing how fidelity degrades with depth and how it improves with better control. They compare multiple metrics, not just one score, to reduce the chance of gaming. They report raw counts, not only processed summaries, so that other groups can reanalyze. The goal is not to demand blind trust. The goal is to make trust auditable. They also test against known classical simulators at the largest feasible sizes, because the best classical attack is part of the experiment's meaning. Tensor network methods can simulate certain circuits efficiently if entanglement is limited, or if the layout can be cleanly partitioned. Schrödinger-Feynman hybrids can trade memory for time, slicing the circuit into pieces and recombining partial amplitudes. These methods are impressive, and their progress is part of the story's suspense. Each new simulator redraws the map of what counts as beyond reach. So experimentalists choose circuit layouts that defeat those simulators, and they do it with a strategist's attention to geometry. They increase depth to raise entanglement across the chip, making it harder to cut the system into weakly connected regions. They choose connectivity patterns that prevent easy partitioning, and they vary gate choices to avoid repeated motifs. In visuals, the circuit diagram becomes a dense tapestry, with entangling links crisscrossing like a storm of threads. But deeper circuits increase error, and that is the trap that defines the advantage regime. If the circuit is too shallow, classical simulation is easy, and the benchmark loses its bite. If the circuit is too deep, noise washes out the quantum signal, phases randomize, and the output becomes close to uniform. Uniformity is the enemy of verification, because many tests lose contrast when everything looks equally likely. The experiment must balance on a narrow ridge. The advantage regime sits between those failures, and it is narrower than the headlines suggest. It is a window where the circuit is complex enough to be classically hard, yet coherent enough to retain a measurable fingerprint in cross-entropy or heavy output rates. The window is where the drama lives, because it is where physics, engineering, and theory all have to cooperate. 1 extra % of error can close the window. One clever classical shortcut can also close it. This is where the cosmological angle enters, but it arrives through engineering rather than through poetry. The machine is a controlled quantum system with many degrees of freedom, and its state lives in a space whose dimension doubles with every added qubit. It produces statistics that imply a high-dimensional structure we cannot directly inspect, like a landscape inferred from shadows on a wall. We cannot print the wave function, and we cannot store it, yet the device behaves as if it is navigating it. The lab becomes a place where the invisible is operational. When the state space becomes too large to write down, language starts to slip, because our instincts are trained on objects we can picture. People ask where the computation is happening, as if computation must occupy a location like a gear train. They ask where the exponential resources live, as if resources must be stored somewhere like fuel in a tank. These questions are natural, and they reveal the strain between mathematical description and physical intuition. They also reveal why interpretations matter emotionally, even when they do not change predictions. Many worlds' language becomes tempting because it offers a location for the exponential, a narrative container for the vastness. The computation is spread across branches, and interference recombines them, and the answer we see is the branch we end up in. It is a story that feels proportional to the scale of the mathematics, and that is why it persists. It gives the mind somewhere to put the two in. It also raises a quiet question. Are we explaining, or just relocating our confusion? But the formalism does not require that story, and the experiment does not endorse it over its rivals. The same unitary evolution and Born rule describe the experiment under any standard interpretation, whether collapse is fundamental or emergent. The device implements a circuit in Hilbert space, then returns samples from measurement, and the statistics agree with quantum theory either way, so the pressure is interpretive, not mathematical. The machine forces us to confront the formalism's scale, but it does not tell us what the scale is. When we cannot verify by full simulation, we lean on what we think the wave function represents, even if we pretend not to. If it is real structure, then the device is steering something vast, and the vastness is part of the world. If it is only a predictive tool, then the vastness is in our description, not in the world, and the world remains single and economical. Yet the tool keeps paying rent in the lab, producing distributions that resist classical reproduction. The line between description and ontology becomes harder to keep clean. This is the central question, sharpened by practice rather than by armchair debate. When a quantum computer produces results beyond practical classical verification, is it exploiting quantum mechanics inside one universe? Or is it evidence that computation is distributed across parallel realities, with our observed outcome as one thread among many? The chapter cannot answer that directly, because the experiments do not discriminate, and they were never designed to. What they do is force a new standard of evidence, and that standard has philosophical consequences. We accept that some claims will be supported by statistical tests plus hardness assumptions, and we accept it because the alternative is to stop at the edge. That acceptance is not surrender, but it is a change in scientific posture, and it deserves to be named. We move from direct prediction to indirect certification, where the goal is to rule out broad classes of classical explanations. We move from reconstructing the state to bounding what the state could be, given the observed fingerprints. It is still science, but it is science under computational constraint. There are stronger verification ideas in principle, and they show what is missing when we rely on patchwork. Interactive proofs can let a classical verifier check a quantum prover with limited quantum capability, turning verification into a dialogue rather than a simulation. Cryptographic protocols can certify certain computations under assumptions, so that cheating would imply breaking a hard cryptographic problem. These methods are conceptually powerful, and they hint at a future where trust is formalized. But they are not yet the default for near-term devices. They often require fault tolerance, or special architectures, or additional trusted quantum components, and those requirements are not trivial. For now, verification remains a patchwork, stitched from calibration, smaller instance checks, and statistical correlations. The patchwork is still meaningful if we are honest about what it certifies, and if we resist the urge to oversell. It certifies that the device is not behaving like simple noise, and that it is not merely a classical random number generator in disguise. It certifies that the device maintains multi-qubit coherence beyond trivial scales, long enough to imprint a non-uniform fingerprint. It also certifies that classical simulation is becoming a practical bottleneck, which is a real engineering fact even when theory remains conditional. Even if a clever simulator can match one experiment, the general trend is that quantum hardware is approaching regimes where classical tracking is prohibitively expensive. That trend matters because it changes what counts as a laboratory and what counts as an experiment. The quantum processor becomes an experimental system whose behavior is defined by a circuit description, and the circuit is both the probe and the preparation. Running the circuit is like probing a complex material, except the material is the wave function itself shaped by gates and read out by measurement. So the output bit strings are not the whole story, and they are not the point by themselves. The story is the distribution, and the distribution is a shadow of an internal evolution we cannot fully reconstruct. We learn about the evolution by asking it many questions and looking for consistent answers, and by watching how the shadow changes when we tilt the light. Consistency tests become a kind of scientific contract between the builder and the skeptic, and the contract is written in scaling laws. If you change the circuit slightly, the output statistics should change in predictable ways, not randomly. If you scramble phases, interference patterns should shift, not disappear, unless decoherence is dominating. If you reduce depth, classical simulators should catch up, and the metrics should reflect that convergence. If you increase depth beyond coherence, the distribution should drift toward uniformity, and the correlation scores should decay. These are sanity checks, not proofs, but sanity checks are how science survives in hard regimes. The deeper worry is that sanity checks can be satisfied by multiple models, and the worry is not paranoia. A noisy quantum circuit and a classical approximation might both produce similar cross-entropy scores, especially when noise is high. The more indirect the test, the more room there is for mimicry, and the more careful we must be about what the test actually constrains. This is why researchers emphasize scaling behavior, not one-off numbers that can be flukes. They look for trends across qubit counts and depths, and they look for a widening gap between quantum sampling time and classical simulation time. A widening gap is not only a performance milestone, it is a philosophical milestone, because it stretches verification to the edge, and it asks us to decide what kind of evidence we accept. At the edge, we are forced to admit that some truths may be supported by a mesh of arguments rather than a single decisive check. The documentary's hook returns in a sharper form, because the emotional core is not speed. Machines in extreme cold are returning answers classical physics cannot feasibly reproduce, and our usual audit trail is breaking under the load. At this point, the many-world story gains emotional leverage, and we should notice why it feels persuasive. If the computation seems too large for one world, parallel worlds feel like an explanation that matches the scale. If the wave function is a real object, then perhaps the device is exploiting its full structure, and perhaps that structure is literally realized. But we must keep the boundary between leverage and logic because seduction is not evidence. Quantum advantage does not prove many worlds, because the same statistics arise in one-world interpretations that treat collapse differently or treat the wave function as epistemic. Still, the interpretive pressure is not a mistake, and it tells us something real about the formalism we're using. The mathematics demands an exponentially large state description, and it demands it even when we refuse to picture it. If we treat the formalism as more than bookkeeping, the world is stranger than classical intuition, and the strangeness is operational. The chip does not care which story we tell. It cares about coherence times, gate fidelities, and the unforgiving arithmetic of error accumulation. So the chapter ends with a controlled unease, because the triumph carries a warning about the future of evidence. We can build devices that push beyond classical reproducibility, and we can validate them only indirectly, by statistical fingerprints and theoretical hardness. That is a triumph, because it shows we can engineer quantum behavior at scale. It is also a warning because it shows that verification will increasingly resemble inference under constraint. As quantum processors scale, verification becomes less like checking arithmetic. It becomes more like trusting a theory under stress, while continuously testing for cracks. This is the transition to fragility. These feats occur despite noise and decoherence, and they survive only in a narrow window where coherence outpaces error. The next mystery is how error correction can stabilize such delicate physics long enough to do useful work, not just impressive sampling. If quantum advantage is the first step beyond verifiability, fault tolerance is the attempt to live there, day after day, computation after computation. It is the attempt to make the quantum world reliable, not just surprising. It is where the story turns from sampling to engineering reality itself, because error correction is a way of sculpting dynamics so that information survives. And the central question follows us into that next chapter, because it refuses to stay philosophical. When we can no longer fully verify what the machine did, we will argue about what the machine is. We will argue about what counts as one world and what counts as evidence, when the evidence is a shadow we can only sample. Quantum advantage exposed a new boundary, where outputs arrive faster than full classical auditing, and that boundary feels like a cliff edge. Error correction is what happens when engineers refuse that boundary and demand reliability anyway. A quantum computer fails for ordinary reasons that become fatal at scale, because the state is both delicate and distributed. Decoherence entangles qubits with uncontrolled degrees of freedom, turning phase into inaccessible correlations that no controller can retrieve. Gate errors tilt intended rotations, miss time pulses, and mistuned couplers, so unitary intent becomes drift across many layers. Crosstalk couples, neighbours that were supposed to stay independent so one operation writes faint shadows on many qubits at once. Leakage pushes population out of the computational subspace, so a qubit stops being a qubit in the language the code expects. Measurement error flips readout results, so the final classical record lies about the quantum state, even when the state was fine. Visually, this looks less like a single catastrophe and more like a slow fog creeping in. On a chip diagram, control lines glow and fade, while tiny phase arrows wobble, as if nudged by invisible hands. In the refrigerator's darkness, thermal photons are rare yet not absent, and rare events become inevitable when repeated millions of times. The environment is the silent adversary behind all of these failure modes, and it does not need to be loud to win. Every stray photon, phonon, defect mode, or two-level system can steal witch path information from a superposition. Every stolen bit of witch path information is an unwanted measurement, and measurement is where interference dies. In hardware terms, the enemy has many faces, and each one leaves a different fingerprint. Energy relaxation, called T1, drains an excited state toward the ground state, and it turns quantum computation into a slow leak. Defacing, called T2, scrambles relative phase without changing energy, and it erases the very interference patterns algorithms rely on. Even the best devices fight 1F noise, fluctuating magnetic fields, and microscopic defects that behave like little resonators. This is where the documentary's tension begins. The same measurement problem that fuels many worlds also fuels engineering, because noise is measurement without permission. A qubit is not merely disturbed, it is partially interrogated by a universe that never stops asking questions. Classical error correction feels intuitive because copying is allowed, and redundancy is almost free. You repeat a bit 3 times, vote, and recover from a flip because the information can be duplicated without consequence. Quantum mechanics forbids that move at the foundation, because unknown states cannot be cloned. The no-cloning theorem is not a technical inconvenience. It is a structural rule of the theory, and it is proved from linearity itself. In classical systems, you can also check a message without changing it, because reading a bit does not rewrite the bit. In quantum systems, the act of learning is physical, and physical interactions generally disturb what they touch. That is why quantum error correction sounds impossible in one sentence. Protect quantum information without copying it, and without learning what it is. The trick is that redundancy does not mean duplication of a state, and it never did in the quantum version. Redundancy means encoding one logical qubit into a larger entangled state of many physical qubits, so the information becomes relational. The information becomes non-local, spread across correlations that no single qubit carries by itself, like a melody carried by harmonies rather than a single note. A useful way to picture it is to imagine the logical qubit as a pattern drawn across a lattice. Each physical qubit is a pixel, but the image is not stored in any one pixel's brightness. The image is stored in how pixels agree, disagree, and constrain one another across the grid. A logical qubit is not a beta qubit, and it is a pattern that lives inside a code space. It is a subspace carved out of a larger Hilbert space, chosen so that common errors push the state into distinguishable side spaces. Those side spaces are not abstract bookkeeping. They are places the state can fall into, and places we can detect. Historically, this idea arrived as a shock because it rewired what protection could mean. In the mid-1990s, codes like Shor's 9-qubit code and Steen's 7-qubit code showed that quantum information could be stabilized in principle. Soon after, the threshold theorem sharpened the claim. Below a certain noise rate, arbitrarily long computation becomes possible with sufficient overhead. In this picture, errors are not mysterious, even when the device physics is messy. A bit flip error is a poly X acting on one physical qubit, swapping just orbe and just one in the computational basis. A phase flip error is a poly Z acting on one physical qubit, changing the sign of just one relative to 1, 0. Real hardware produces mixtures and coherent combinations, but the code is designed to diagnose a basis of errors, then build up to the general case. There is a subtle point hiding in that word diagnose. The code does not identify an error by peeking at the logical state, because that would destroy what it tries to protect. Instead, it extracts a syndrome, a classical record that labels which constraints were violated. The syndrome is information about the damage, not information about the message. The key move is separating two kinds of information, and the separation must be physical, not rhetorical. There is the encoded quantum information that must remain hidden to preserve superposition, because amplitudes are the computation. There is the error information that must be extracted to preserve the computation, because uncorrected drift accumulates. Quantum error correction is the art of extracting the second while shielding the first. Syndrome measurement is the mechanism that makes that separation real, and it is where the shouldn't work feeling peaks. You measure operators that reveal whether an error occurred without revealing the logical state itself. You learn about parity and consistency, not about amplitudes and phases. This is allowed because the measured quantities commute with the logical information, meaning they can be known simultaneously. The stabilizers are designed so that measuring them projects onto an error syndrome, not onto a computational answer. The measurement collapses something, but it collapses only the error subspace label, leaving the logical amplitudes untouched. That sentence is the loophole that feels like cheating, because it uses measurement as a tool rather than a terminal event. Measuring usually destroys quantum information, yet here measurement is used as a shield. The shield works because it is pointed at the right variables, like listening for a crack in a violin string without listening to the music. To see why, we need a clean distinction between measuring a qubit and measuring a relation, because the relation can be classical even when the state is quantum. A direct measurement asks whether a qubit is 0 or 1, and it reveals the state in that basis. A stabilizer measurement asks whether 2 or 4 qubits agree in parity, and it reveals only a constraint. The constraint is a yes or no fact about correlations, not a readout of the encoded message. In practice, the code uses ancilla qubits as probes, and the probes are sacrificed for information. The ancillas interact with data qubits through controlled gates, then the ancillas are measured. The data qubits are not directly measured, so the encoded state can survive, even as the machine constantly produces classical bits. Visually, the ancillas look like little messenger particles moving through a grid. They touch a set of data qubits in a precise order, then vanish into a measurement pulse, leaving behind a single bit of syndrome. Round after round, the lattice blinks with these tiny interrogations, like a city seen from above at night. But survival is not passive, and the code is not a protective coating you paint on top. The syndrome outcomes drive active correction, applied as conditional operations or tracked in software as a Pauli frame. The system becomes a feedback loop where measurement is continuous and controlled, and where classical electronics become part of the quantum machine. A Pauli frame is an especially revealing idea because it shows how much of correction is interpretation. Instead of physically applying every corrective X or Z, the controller can update a record of what the logical state means in the chosen frame. Later gates and measurements are adjusted accordingly so the computation stays consistent without extra noisy operations. The deeper point is that quantum information is not stored in any one place, and that is why it can be repaired. It is stored in a geometry of entanglement that can be patched, as long as damage stays below a critical density. When errors remain sparse, they look like isolated scratches on a pattern, not like a tear that splits it. Error correction also reframes decoherence, and it does so in a way that feels almost philosophical. Decoherence is entanglement with the environment, which looks like measurement from the inside of the system. Error correction is entanglement with chosen ancillas, which looks like measurement we can compensate. The difference is not whether entanglement happens. The difference is whether we control the record it creates. This is the transition to evidence. If we can stabilize fragile superpositions by extracting only syndrome information, then the wave function starts acting like an engineered object. It stops being merely a symbol on paper and starts behaving like something we can maintain, tune, and keep alive. The most influential family of codes for near-term hardware is the surface code, partly because it respects the brutal realities of fabrication. It fits naturally on a two-dimensional grid with local interactions, which matches many superconducting layouts. It uses repeated measurements of plaquette and star operators, turning the chip into a lattice of parity checks that never sleep. Surface codes are built around a simple idea, but the simplicity hides a deep statistical promise. You increase code distance, meaning the size of the smallest error chain that can cause a logical failure. If physical errors are sparse enough, larger distance makes logical errors exponentially rarer because the system demands a longer, more coordinated accident. A useful visual is a rainstorm on a tiled roof. A few drops landing on tiles do not matter because the roof structure routes them away. A leak appears only when drops align into a path that crosses a seam, and that alignment becomes unlikely when the roof is larger and better sealed. That sparsity condition becomes a threshold, and it is one of the most consequential ideas in quantum engineering. Below a certain physical error rate, adding more qubits and more checks improves the logical qubit. Above that threshold, adding more hardware just adds more places to fail, and the code becomes a large target. The threshold is not a single number that applies to every device, and engineers learn that quickly. It depends on noise bias, leakage, measurement fidelity, crosstalk, and how well errors are independent in space and time. But the existence of a threshold is the conceptual miracle, because it says reliability can emerge from unreliable parts. It says there is a regime where complexity buys reliability, even though every component is noisy. That is the opposite of naive intuition about fragile quantum states, where more qubits seems like more ways to lose coherence. Fault tolerance turns that intuition inside out, but only if the noise behaves within the code's assumptions. To make the threshold real, the code must run repeatedly, and repetition is where the machine becomes a dynamical system. Each round of syndrome measurement produces a pattern of bits across the lattice. A decoder then infers the most likely error configuration consistent with those syndromes, often using algorithms inspired by statistical physics. Decoding is classical computation, and it becomes part of the quantum computer's nervous system. The quantum hardware generates syndromes, and the classical controller interprets them in real time. The boundary between quantum and classical becomes an engineered interface, not a philosophical line, and latency becomes a physical parameter. The decoder's job is not to find the true error history, because it cannot, and it does not need to. The decoder's job is to find a correction that keeps the logical state in the code space, so future operations behave as intended. Many different physical error histories can be equivalent at the logical level, and the code cares only about that equivalence class. This is where non-locality becomes practical, and the word stops sounding purely theoretical. A logical error is not one bad gate. It is a connected chain of local errors that wraps across the code. The code turns local noise into a global event that is statistically unlikely, and it does so by forcing errors to coordinate across distance. Recent experiments aim at one question, not a marketing claim, and the question is brutally specific. Do logical error rates actually fall as code distance increases, once you include real hardware imperfections and real decoding? The answer must be a scaling law, not an anecdote, because a single low-error run proves nothing. The early trend lines were ambiguous, because leakage and correlated noise can defeat the assumptions in quiet ways. Crosstalk can create bursts of errors that look like chains, and bursts do not thin out with distance as quickly. Measurement errors can inject false syndromes that mislead the decoder, causing it to correct in the wrong direction. So the field learned to treat error correction as a full-stack problem, not a code you bolt on at the end. You need better physical qubits, better calibration, better couplers, better readout, and better decoding. You also need to design the code cycle so that the act of checking does not create more errors than it detects. In superconducting devices, the stabilizer cycle is a choreography of microwave pulses and idling periods, and the choreography must be exact. 2-qubit gates are the main source of error, so the schedule matters as much as the gate design. If the schedule creates spectral crowding or residual coupling, the code can fail even below nominal error rates. Visually, this choreography can be shown as a timed score, like music written across many staves. Pulses strike, couplers open, qubits idle, and readout resonators ring, while the refrigerator's cold stage holds everything near absolute zero. Under that calm, the system is racing, because error correction is a contest of timescales. Leakage is especially dangerous because it breaks the Pauli error model that makes decoding efficient. a leaked qubit can poison multiple checks, spreading errors through the circuit and creating patterns that mimic long chains. Modern experiments add leakage reduction units and tailored decoding rules, treating leakage as a first-class noise channel rather than an inconvenience. When the code works, the evidence is not a single run, and it is not a single impressive circuit. The evidence is a scaling law, where logical error per round decreases as distance increases. That is the signature of being below threshold, and it is the closest thing to a certificate a quantum machine can offer. This matters for the documentary's central question, because it changes what a quantum computer is doing in time. Without correction, the machine is a short-lived interference experiment, beautiful but brief. With correction, the machine becomes a stable dynamical system that preserves an abstract state against the universe, round after round. A logical qubit is also a new kind of object, and it resists the usual metaphors of hardware. It is defined by constraints and symmetries, not by a localized degree of freedom. It exists only because many physical qubits cooperate, and because measurements continually enforce the code space, like a rule that is reasserted every moment. That enforcement sounds like collapse, yet it does not collapse the computation, and that is the paradox the camera should linger on. It collapses the system onto a protected subspace, while leaving the logical amplitudes intact. The machine is measured constantly, and still it behaves quantum mechanically, as if observation has been domesticated. This is the part that should not work if classical intuitions were fundamental, because classical protection relies on copying and isolation. Classical intuition says measurement ends quantum behavior, and copying is required for protection. Quantum engineering says protection can come from entanglement plus selective measurement, and the selectivity is everything. At scale, error correction becomes a statement about information as a physical resource, not as an abstract label. The code treats information like something that can be stored in correlations, moved by gates, and repaired by feedback. The environment tries to read it, and the computer refuses, by continually reasserting which questions are allowed. That refusal is not metaphysical, but it touches metaphysics, because it forces us to ask what is being protected. If the wave function were only bookkeeping, error correction would look like bookkeeping protecting itself with clever accounting. If the wave function is real structure, error correction looks like building scaffolding in that structure, then maintaining it against erosion. Many worlds language returns here with new force, because the code manipulates branches without letting them decohere too quickly. The code keeps alternative histories coherent long enough to correct them, then recombines them into a stable logical trajectory. If branches are real, the code behaves like a protocol that keeps them aligned long enough to be useful. A one-world instrumentalist can still describe the same process, and the mathematics does not change. The state is a tool, and the tool is updated by syndrome measurements that reveal only error data. But the tool now behaves like an engineered medium, and the line between tool and thing blurs because the medium has stability and dynamics. A bowman can also tell a story, where the pilot wave in configuration space is stabilized by the code's constraints, and where the guiding structure is continually reinforced. A collapse theorist must explain why constant syndrome measurement does not trigger collapse of the logical state, even though it is measurement in a literal laboratory sense. Error correction does not pick an interpretation, but it stresses them differently, like a load test on a bridge. The engineering fact remains, and it is the fact that motivates entire roadmaps. Fault tolerance predicts that once below threshold, arbitrarily long computations become possible in principle. The cost is overhead, because one logical qubit may require thousands of physical qubits, plus the machinery to keep them synchronized. The payoff is that computation becomes a controllable process, not a fragile stunt. The overhead is not only qubits, and it is not only a number on a slide. It is wiring, cryogenic load, control electronics, calibration time, and decoding latency, all of which must scale without collapsing under their own complexity. Error correction is the bridge between laboratory demonstrations and machines that can run for hours, and the bridge has to carry weight. It also reshapes verification, and this is where the earlier boundary reappears in a new form. A fault-tolerant machine can run circuits too deep to classically simulate and still claim correctness through its own internal checks. The machine becomes self-certifying in a limited sense, because syndromes bound the logical error rate, and because those bounds can be tracked over time. That self-certification is not absolute, because correlated noise and model mismatch can still hide in the cracks. A decoder can be fooled by patterns it was not designed to expect, and a device can drift in ways that violate the assumed statistics. But it is a new kind of evidence, derived from the machine's ability to police itself, and it changes the epistemology of computation. The computer becomes both experiment and error-detecting instrument, and that dual role is visually striking. The same chip that runs an algorithm also runs a diagnostic lattice, and the diagnostic never stops. In the control room, syndrome streams scroll like telemetry from a spacecraft, because the computation is also a continuous health check. This pushes the documentary toward its climax. We started with refrigerators that delay measurement, and we end with architectures that weaponize measurement. We began by hiding from the environment, and we now build feedback loops that outpace it, turning observation into a stabilizing force. If information can be protected without copying, then information is not a classical substance, and that is the pivot. It is a quantum pattern that can be distributed, constrained, and repaired. The universe permits that pattern to persist, even while forbidding the simpler classical trick, and that permission feels like a clue about the rules underneath. So the chapter closes on a philosophical pivot that is not optional anymore, because the engineering has made it concrete. If quantum information can be stabilized and manipulated at scale, then information behaves like a physical ingredient. It can be conserved globally, hidden locally, and made robust through entanglement, even when the parts are noisy. That implication reaches beyond computation, and it echoes ideas already present in theoretical physics. Cosmology already treats the universe as an information processing system. From black hole entropy to holographic bounds, error correction suggests that the universe may protect information through structure, not through isolation, and that protection may be woven into geometry itself. In that light, quantum error correction stops looking like a hack and starts looking like a clue. Reality may be built so that information can be preserved in non-local ways, even when local pieces are noisy and exposed. What looks like fragility at the microscopic level may coexist with stability at the encoded level. The central question returns with sharper edges, because the machine now seems to do something almost self-consistent. When a quantum computer produces results beyond practical classical verification, is it exploiting quantum mechanics inside one universe? Or is it coordinating computation across parallel realities, with error correction acting like the protocol that keeps branches aligned? We cannot answer that here, but we can name what has been proven in practice, and what remains an open demand. Engineers can build logical qubits that are more stable than their parts by measuring without learning. They can turn the act of observation into a shield, and that should change how we think about what is real. Next, we follow that change outward. If information is physical and protectable in ways classical intuition rejects, then the universe itself may be an error-correcting medium. The final chapters ask what that means for time, gravity, and the meaning of one world. In rooms colder than deep space, quantum machines output ordinary bits with extraordinary origins, and the air itself seems to hold its breath. Stainless steel cylinders loom like silent engines, wrapped in cables and microwave lines that vanish into the ceiling. Inside, dilution refrigerators push matter toward millikelvin temperatures, where thermal noise quiets enough for fragile quantum states to persist. The bits that emerge look mundane on a screen, yet their ancestry is stranger than any classical circuit. Those bits are not only physics results now, they are pressure on the systems that keep modern society coherent. Encryption is where abstract amplitudes become a concrete vulnerability, because trust is built from math rather than handshakes. Every secure website, software update, bank transfer, and diplomatic cable depends on keys that must remain unguessable. The public sees a padlock and a reassuring green indicator, and the moment feels personal and local. Institutions see a fragile chain of assumptions: hardware, software, protocols, and the belief that certain computations stay expensive. That belief is not sentimental. It is a budget line, a risk model, and a promise to citizens. Modern cryptography works because some problems look easy one way and brutal the other, even when you know the rules. Multiplying two large primes is fast on any laptop, and the result fits neatly into a few hundred bytes. Factoring their product appears to require astronomical work on classical machines, because the best-known methods scale badly as numbers grow. The asymmetry is the point. The lock is easy to build, yet painfully slow to pick. For decades, that imbalance has been stable enough to underwrite global commerce. Public key cryptography turns that asymmetry into a social tool, and it solves a problem older than the internet. You publish a public key that anyone can use to encrypt, even if they have never met you. You keep a private key that only you can use to decrypt, and the separation lets strangers coordinate securely. In practice, it also enables digital signatures, which are the cryptographic equivalent of sealing wax and handwriting. A signature says, in mathematics, that a message came from the holder of a secret and was not altered. RSA is the most famous example, and its core is factoring, a problem studied long before computers existed. Choose two secret primes and multiply them into a modulus, typically thousands of bits long. The public key exposes the modulus and an exponent, while the private key depends on the primes and related values derived from them. The security intuition is simple enough to say aloud. If you cannot recover the primes, you cannot reconstruct the private key efficiently. Diffie, Hellman and related schemes rely on a different hardness story, but the social effect is similar. They use discrete logarithms in finite groups, often modulo a prime, where arithmetic wraps around like a clock. Computing a power is easy, even for huge exponents, because algorithms exploit repeated squaring. Reversing it without the secret appears infeasible classically, because there is no known shortcut comparable to factoring tricks. Diffie and Hellman's 1970s insight was political, as well as technical. It offered secure key agreement without couriers, and it changed what mass communication could safely be. Elliptic curve cryptography compresses the same idea into smaller keys, and that compression matters at scale. The hard problem becomes discrete logs on elliptic curves, where the group operation is geometric and algebraic at once. The security per bit is higher, which is why phones and servers adopted it, especially when bandwidth and battery life were tight. A smaller key reduces handshake time, storage, and the chance of implementation mistakes. It also makes modern protocols feel instantaneous, which is part of why we trust them. None of this is magic, and none of it is unbreakable in principle, because cryptography is not a law of nature. It is a bet on classical limits, informed by decades of mathematical attack and engineering practice. It is a bet that the best attacks remain too slow for any adversary, including well-funded states. That bet has always been conditional, and cryptographers have never pretended otherwise. They manage risk by choosing parameters that make attacks economically irrational. That bet held because classical computation scales in familiar ways, and the constraints feel tangible. You can buy more servers and wait longer, and you can estimate the cost in electricity and time. But the cost still climbs steeply with key size, and the curve has been forgiving enough to stay ahead. When a key length doubles, the defender's cost rises modestly, while the attacker's rises much more. That is the asymmetry that makes the padlock icon meaningful. Quantum computing changes the shape of that cost curve, and the change is not incremental. Shor's algorithm shows that factoring and discrete logs are not fundamentally hard in the same way we assumed. They are hard only for classical machines, which is a different claim than being hard in nature. The difference is subtle, but it is everything. It means the lock was strong because of our tools, not because of the structure of the problem. Shor's algorithm is not a faster factoring trick in the usual sense, like polishing an old method. It reframes factoring as period finding in a quantum state, where periodicity becomes a measurable resource. Interference amplifies the period, and the period reveals the factors through classical post-processing. The algorithm's power comes from using superposition to evaluate many inputs coherently. It then uses interference to cancel wrong answers and reinforce the hidden structure. The key move is the quantum Fourier transform, which turns hidden periodicity into measurable peaks, like a prism splitting light. The algorithm creates a superposition over many inputs, not as parallel universes doing separate work, but as a single wave function with many components. It computes a function coherently, keeping phase relationships intact, then uses interference to extract structure. Measurement collapses the state, yet the collapse is guided by the engineered pattern of amplitudes. What looks like luck is actually careful choreography. This is where the documentary's tension begins. The same interference that unsettles reality also threatens the math that stabilizes trust, and the connection is not poetic. The cryptographic hardness assumptions that built the internet were never tested against quantum dynamics. Now the physics itself offers a new kind of leverage. The question becomes practical. How quickly can theory become infrastructure? A sufficiently large fault-tolerant quantum computer could break RSA by factoring its modulus, and the statement is precise. The same machine could break Diffie, Hellman and elliptic curves by solving discrete logs, even when parameters are chosen conservatively. One algorithm undermines the dominant public key families at once, and that convergence is what makes the moment dangerous. It is not a niche vulnerability in an obscure protocol. It is a broad fault line beneath the most common trust mechanisms. The phrase sufficiently large hides the real obstacle, which is not the algorithm's existence or even its elegance. It is the engineering cost of running it with low enough error for long enough without losing the computation. Shor's circuit depth is long, and long circuits demand error correction at a scale that current devices cannot sustain. Quantum gates are imperfect, qubits decohere, and small inaccuracies accumulate like static in a long-distance call. Fault tolerance is the difference between a laboratory curiosity and a machine that can threaten institutions. A useful distinction matters here, because headlines blur it, and the blur misleads policy. Physical qubits are the noisy devices in the refrigerator, each one a real object with a real error rate. Logical qubits are encoded patterns protected by continuous syndrome measurement, where many physical qubits collaborate to behave as one. Error correction does not remove errors by magic. It detects them indirectly, using carefully designed measurements that reveal only the error, not the protected information. Shor's algorithm needs logical qubits, not just a few impressive physical qubits displayed on a press release. It needs them stable for millions or billions of gate operations, depending on key size and architecture. That stability is the entire challenge, because a single uncorrected error can poison the final result. The machine must keep coherence while performing an enormous choreography of operations. In classical terms, it is like running a computation where every transistor occasionally lies. Estimates vary, but the order of magnitude is the point, and it keeps planners awake at night. Breaking a 2048-bit RSA key is not a 1,000-qubit stunt, even if 1,000 sounds immense. It is likely thousands of logical qubits and tens of millions of physical qubits, depending on error rates, connectivity, and gate speeds. Some projections are more optimistic, others more conservative, but none are casual. The numbers force a new kind of timeline thinking. The overhead comes from code distance, routing, and the need for magic state distillation, which sounds like alchemy but is bookkeeping. Surface codes trade space and time for reliability, using a grid of qubits and repeated checks to catch errors. The trade is brutal but systematic, and it turns cryptography into a long-range forecast. Even if the physics is sound, the engineering must be scaled like an industrial project. The refrigerator becomes a factory, and the factory becomes a strategic asset. So the threat is not that a lab demo breaks the internet tomorrow, and that nuance matters. The threat is that a future machine breaks the recorded past, because encrypted archives do not expire automatically. The clock starts before the machine exists, because data can be stored cheaply and copied silently. A message intercepted today can become a confession years later, without the sender ever knowing. In that sense, time itself becomes an attack vector. This is the harvest now decrypt later problem, and it is already active in the real world. An adversary can collect encrypted traffic today and store it, whether by tapping fiber, compromising endpoints, or buying access to logs. When quantum decryption becomes feasible, the old ciphertext becomes readable, and the act is almost anticlimactic. There may be no intrusion alert, no malware signature, and no dramatic breach. There is only a database that suddenly yields meaning. The danger depends on how long the information must remain secret, and some secrets have long shadows. Medical records, intelligence sources, and corporate plans can have decades-long sensitivity, especially when they reveal patterns rather than single facts. Even if quantum computers arrive late, the damage arrives immediately, because the harvesting can be done now. A patient's diagnosis, a dissident's contact list, or a negotiating position can be weaponized long after the original moment. What feels like history can become leverage. This changes how institutions think about time, because cybersecurity is no longer only about today's attackers. It is about tomorrow's capabilities applied retroactively to yesterday's conversations, contracts, and authentication logs. It also changes what counts as a breach, which is a legal and cultural shift. No system has to be hacked in the usual sense, and no password has to be guessed. The attacker can simply wait because the mathematics is the lock. Governments noticed this early because signals intelligence is built on stored data and long-term analysis. If you can break old traffic, you can rewrite histories of negotiation and conflict, and you can do it quietly. You can expose sources, methods, and alliances long after the fact, when the people involved assumed the risk had passed. The archival nature of intelligence makes it uniquely vulnerable to delayed decryption. It turns the future into a retroactive surveillance tool, so a quiet race begins, and it is not only about building quantum computers in gleaming labs, it is about migrating the world's trust infrastructure before the deadline, while the deadline remains uncertain. The uncertainty makes planning harder, because budgets prefer dates and engineers prefer requirements. Yet the physics does not offer a calendar invitation. It offers a possibility that grows more plausible each year. The migration is called post-quantum cryptography, and it is mostly classical math rather than quantum tricks. The goal is to replace factoring and discrete logs with problems believed hard even for quantum machines. The replacement must run on today's devices at global scale, from servers to smart meters. It must survive hostile networks, constrained hardware, and the messy reality of software ecosystems. In other words, it must be secure and deployable, which are not the same achievement. Lattice-based cryptography is the leading candidate family, and its intuition can be explained without losing the rigor. It relies on problems like learning with errors, where noise is part of the hardness rather than a nuisance. You are given linear equations with small random errors, and the errors hide the secret like fog hides a landscape. Quantum algorithms do not erase that hardness in the same way Shor erases factoring, at least not with anything known today. The best quantum speedups are partial, not devastating, so parameters can be chosen to compensate. Other approaches exist, and each has trade-offs that become obvious only in implementation. Code-based schemes use error-correcting codes and large public keys, which can stress bandwidth and storage. Hash-based signatures are conservative, but can be stateful or bulky, and statefulness creates operational risk. Multivariate polynomial schemes were once promising, then many were broken, sometimes dramatically, by new algebraic techniques. Isogeny-based schemes looked elegant, then major proposals fell to new attacks, reminding everyone how young this field is. The lesson is that post-quantum is not a label. It is a continuous stress test. Standards efforts try to turn that stress test into policy, because coordination is the real battlefield. NIST has run multi-year competitions to select algorithms for encryption and signatures, inviting public cryptanalysis and formal scrutiny. The process is slow because the cost of being wrong is global, and because confidence is earned by surviving attacks. Cryptographers publish reductions, implementers test edge cases, and adversaries probe for shortcuts. Over years, what remains standing becomes a candidate for trust. The new standards are not only math selections, and that is where institutions often stumble. They are engineering constraints on key sizes, handshake latency, memory, and side-channel resistance, all of which shape real deployments. A secure algorithm that cannot be implemented safely is not secure in practice, because bugs become backdoors. The standards must anticipate how code will actually be written, optimized, and shipped. They must also anticipate the creativity of attackers, who target the weakest link, not the theorem. This is the transition to evidence. Security becomes a chain of proofs, implementations, audits, and institutional discipline, not a single clever theorem. It becomes a culture of updates, key rotation, and monitoring, which is less glamorous than discovery. The strongest algorithm can be undermined by a flawed random number generator or a careless API. The documentary's mystery shifts from pure physics to the sociology of reliability. How do you make billions of devices behave responsibly? Migration is harder than invention, because the internet is not one system with one owner. It is millions of systems with different life cycles, vendors, and incentives, stitched together by protocols and habit. Some devices cannot be updated because they were built cheap or deployed in inaccessible places. Some organizations do not know where cryptography is embedded because it sits inside libraries and dependencies. The result is a map with blank spaces, and blank spaces are where risk hides. Public key cryptography is used in more places than most users realize, and the list is longer than the browser. It authenticates software updates and prevents supply chain poisoning, which has become a central fear of modern security. It secures VPNs, email, messaging, and cloud access, often invisibly. It also protects machine-to-machine communication, where no human is watching for a warning. When that foundation shifts, the effects ripple through automation itself. It also anchors certificate authorities and the web's identity model, which is a delicate hierarchy. If signatures become forgeable, attackers can impersonate services at scale, issuing convincing certificates or faking updates. Trust collapses not with a bang, but with silent substitution, where everything looks normal until it is too late. A user cannot visually distinguish a genuine handshake from a forged one. The browser will still show a padlock, and the illusion will be complete. So institutions plan phased transitions, often called crypto agility, and the term hides hard work. Systems must support multiple algorithms during a long overlap period, because you cannot flip the world in one night. That overlap itself creates new attack surfaces, because negotiation mechanisms can be manipulated. Attackers love transitional states, where compatibility requirements weaken security. The migration must therefore be engineered like a careful bridge replacement, with traffic still flowing. Hybrid handshakes combine classical and post-quantum keys, and the logic is defensive redundancy. The idea is that an attacker must break both to recover the session key, so the system remains safe if either assumption holds. This buys time, but it adds complexity and increases the risk of misconfiguration, especially across diverse clients. It also increases message sizes, which can trigger unexpected behavior in networks. The safest path on paper can be fragile in the field. Complexity is where real failures happen, and history is clear on that with painful examples. Many cryptographic disasters were not broken math, and they were not even sophisticated. They were broken implementations, bad randomness, and side channels, where secrets leak through timing, power use, or cache behavior. The attacker does not need to solve the hard problem if the device whispers the answer. Security engineering is therefore as much about silence as it is about strength. Post-quantum schemes bring new implementation risks, and they arrive with new kinds of performance pressure. Lattice algorithms can leak secrets through timing and cache patterns, especially when code branches on secret-dependent values. Constant time coding becomes mandatory, and it's easy to get wrong when optimizing for speed. Even memory access patterns can betray information, which forces developers to think like adversaries. The math may be sound while the code is porous. Key sizes can be larger, and larger messages can trigger protocol edge cases that were never exercised. Network middle boxes can break unfamiliar handshakes because they were built to recognize old patterns and sometimes interfere. Embedded devices can fail under memory pressure, and failure modes can become security holes. A system that crashes during a handshake may fall back to weaker settings. The transition therefore becomes a test of the internet's hidden assumptions. Even the best migration plan must confront human factors, because security is executed by people under deadlines. Administrators copy configurations without understanding them, and small mistakes can propagate across fleets. Vendors ship defaults that prioritize compatibility, because support calls are expensive and outages are visible. Attackers exploit the gap between theory and deployment, where the real world is always messier. The documentary's unease grows here, because the vulnerability is not only technical, it is organizational. There is also a geopolitical layer that cannot be ignored, because cryptography is both a shield and a bargaining chip. Standards are global, but trust is not, and nations worry about hidden weaknesses and asymmetric readiness. Some fear backdoors, while others fear being left behind in the transition. Quantum capability becomes a strategic ambiguity, like stealth or code breaking in earlier eras. A state that can decrypt quietly gains leverage without revealing it, so secrecy becomes rational. That secrecy feeds the harvest now decrypt later logic, and it makes the race feel circular. If you believe an adversary might already be close, you collect more now, because the payoff could be enormous. If you believe you might be first, you want more stored targets later, because archives become future power. So the quiet race is not only laboratories competing for qubits, it is agencies competing for archives, and it is companies competing to migrate without breaking services. It is a global scramble to replace a foundation while standing on it, and the metaphor is literal. The internet's trust layer is not a feature you can uninstall. It is woven into protocols, devices, and legal expectations, and it is embedded in hardware security modules and smart cards. The replacement must happen while transactions continue and while adversaries watch for confusion. Every step must preserve continuity, because society does not pause for cryptography. That pressure is what makes the race quiet rather than theatrical. This pushes the documentary toward its climax. Quantum mechanics stops being a strange theory in textbooks and becomes a force that rearranges institutions, budgets, and alliances. The camera can linger on ordinary scenes, an ATM, a hospital terminal, a customs checkpoint, because each one depends on invisible math. The mystery is that the math feels timeless, yet it is contingent on physics. When the physics changes what is feasible, the social contract changes with it. The link back to physics is not metaphorical, and it is not optional. Shor's algorithm works only because amplitudes interfere across an exponentially large state space, even though we cannot see that space directly. The same formalism that made verification hard now makes encryption brittle, and the symmetry is unsettling. We built trust on computational difficulty, then discovered a machine that reshapes difficulty. The universe did not promise us one-way functions. We inferred them from our limitations. We returned to the central question through a different door, and the question now has teeth. When a quantum computer outputs a factorization we cannot feasibly reproduce classically, what exactly did the machine do? Did it exploit one universe's wave function? Or did it coordinate across branches, as some interpretations tempt us to say? The documentary does not need to settle the metaphysics to feel the weight. Cryptography makes that question feel less optional, because trust demands certainty. Yet quantum advantage taught us that certainty can become indirect, and society already lives with that compromise. We accept statistical fingerprints and hardness assumptions when direct simulation fails, and we call that acceptance rational. We trust that a protocol is secure because it has resisted analysis, not because we have exhausted all possibilities. Now society faces a parallel dilemma. We cannot wait for perfect proof of future quantum capability, because perfect proof may arrive too late. We must act under uncertainty, because the cost of waiting is irreversible exposure, and exposure cannot be recalled. Post-quantum migration is therefore a civilizational experiment in inference, conducted in procurement documents and engineering roadmaps. Institutions must decide what to trust when the threat is predicted by theory and partial evidence. The choice is made in standards meetings, product cycles, and long-term contracts. It is made by people who may never see a quantum computer, yet must plan for one. The irony is that cryptography was built to create trust between strangers, and it succeeded so well that we forgot it was fragile. Quantum computing forces strangers to coordinate a transition together because the network is shared. The same physics that enables new computation also destabilizes the social fabric of verification, and the destabilization is subtle. It appears as policy memos, new cipher suites, and compatibility warnings. It appears as a slow retooling of the world's quiet machinery. There is a deeper symmetry with earlier chapters, and it is unsettling once you notice it. Error correction used measurement as a tool without learning the protected state, which sounds paradoxical, but is operationally precise. Post-quantum cryptography uses public information to protect private secrets, which is also paradoxical in ordinary language. Both are architectures of selective knowledge, designed to reveal what is necessary and conceal what is dangerous. Both depend on what can be learned without destroying what matters. Both reveal that information is physical, and that physics sets the terms, even when the interface looks purely digital. If the quantum state is only bookkeeping, then Shor's algorithm is a remarkable shortcut in our predictions, a new compression of computation. If the quantum state is real structure, then the shortcut is a new way to steer that structure, and the steering has consequences. Either way, the consequences land in courts, banks, and treaties, where uncertainty is expensive. What began as a phase relationship in a refrigerator becomes a change in institutional behavior. So the chapter ends with a quiet unease rather than a loud warning, because the danger is not cinematic. The terrifying part is not that quantum computers will break locks, as if the world simply needs stronger locks. The terrifying part is that reality's rules can rewrite trust at scale, and the rewrite can be silent. How many of our other assumptions are merely temporary agreements with physics? How many of our institutions rest on limits that might shift? Next, we follow that change outward. If quantum theory can destabilize encryption, it can destabilize any institution built on classical limits, even if the connection is not obvious. The final chapters ask what else those limits were quietly holding together, and what happens when the quiet race reaches the rest of society. We return to cosmology with a new suspicion, and it feels less like metaphor than diagnosis. Computation is not outside physics, and physics may be computation in disguise. The question is not poetic because every calculation is a physical process. Charges moving, photons scattering, atoms settling into states. Landauer's principle draws the first hard line, and it arrives with the bluntness of a laboratory result. Erasing one bit costs energy, because information is embodied in microscopic degrees of freedom. When a memory is reset, many possible microstates are forced into one, and entropy must be paid elsewhere. Memory is never free, and forgetting is a thermodynamic event that leaves heat behind. In practice, the cost is tiny, yet it is universal, and it ties logic to temperature. That claim scales upward into a cosmic question, and the camera can pull back from a circuit to a galaxy. If information has a price, then the universe keeps accounts, even when nobody watches. The refrigerator and the qubit are not exceptions. They are local negotiations with the same bookkeeping trading order here for disorder there. Even our most abstract software runs on matter, and matter keeps receipts. Quantum field theory sharpens the unease because it refuses to grant us a truly empty stage. Empty space is not empty, because fields have a ground state with unavoidable fluctuations. The vacuum is a structured state filled with correlations that can be measured indirectly. In the lab, effects like the Casimir force hint at that restless background, as plates feel a pressure from modes that cannot fit between them. Those fluctuations are not just noise, and the visuals can linger on a dark void that never stays still. They set baselines for particle behavior, renormalization, and the energy density we argue about in cosmology. Even the word vacuum becomes misleading, because the lowest energy state still carries activity. Virtual excitations appear and fade, constrained by uncertainty, and the bookkeeping remains consistent even when the events are unobserved. In cosmology, vacuum structure becomes destiny, and the early universe turns into a kind of amplifier. Inflation models lean on quantum fluctuations to seed later structure, then stretch them across the sky. The early universe turns microscopic randomness into macroscopic pattern, and we still live inside the imprint. What begins as a jitter in a field becomes a slight overdensity, then a filament, then a cluster of galaxies. When we map the cosmic microwave background, we are reading a fossil record of that amplification. Entanglement then enters gravity, carefully and without promises, like a concept walking into a room it may not own. In holography, entanglement entropy tracks geometry in certain models, linking boundary information to bulk spacetime. In quantum gravity discussions, spacetime sometimes looks like a code protecting information. The imagery shifts to a lattice of connections, where distance is not drawn first, but inferred from how strongly parts of the system share correlations. What is known is narrow but real, and it matters because it is calculable rather than rhetorical. Entanglement entropy is computable in specific frameworks, and it organizes how regions share information. It behaves like an accounting tool for correlations, telling us what can be learned locally and what is irreducibly shared. What is speculative is the leap from those frameworks to our universe, and researchers argue about the bridge. The temptation is enormous because geometry feels fundamental, yet information may be the deeper currency. This is where the documentary's tension begins. Quantum computers may be probes of the same entanglement structure because they engineer correlations that classical descriptions cannot track. On screen, a dilution refrigerator becomes a quiet cathedral of metal, with cables descending like roots into a cold that suppresses thermal noise. Gates click in sequences that are invisible, while the state space grows too large to picture directly. The machine does not merely compute faster, it explores a different geometry of possibilities, but interpretation returns because the math stays silent about meaning, and the same predictions wear different stories. Many Worlds says the wave function never collapses, and computation is interference across branching records. It pays by multiplying realities, then tries to recover probability as rational self-location. Historically, it echoes Everett's mid-century proposal, once dismissed as extravagant, now revived by the sheer success of unitary quantum mechanics. Objective collapse models pay a different price, and they do it by changing the rules rather than the story. They add new dynamics that force real collapse, often tied to mass, scale, or gravity. They aim to explain definite outcomes, but must fit existing experiments and avoid breaking energy accounting. Their promise is clarity, yet their burden is precision, because the world has already tested quantum theory with ruthless accuracy. Bohmian mechanics keeps one world, but adds hidden variables and a non-local guiding wave, and the visuals can show a single path through a fog of alternatives. It explains outcomes with trajectories, yet accepts that the pilot wave lives in configuration space. The cost is explicit non-locality that cannot be used for signaling. It preserves determinism, but it relocates strangeness into a higher dimensional guidance field. Cubism and other epistemic views shift the target, and they do it by shrinking the wave function's job description. The wave function becomes an agent's expectations, not a cosmic field. They dissolve some metaphysical claims, but they inherit the task of explaining why agents share stable, law-like statistics. If quantum theory is partly about belief, then the universe still must explain why those beliefs converge and why experiments remain stubbornly reproducible. This pushes the documentary toward its climax. When outputs outrun verification, we ask what quantum computers have actually proved, not what we want them to mean. A histogram on a screen is not a multiverse, and a successful sampling task is not a philosophical verdict. The devices deliver statistics, and statistics demand interpretation, but they do not choose one for us. They have not proven parallel universes, because interpretations largely agree on circuit statistics. They have proven that quantum information is physical, costly, and controllable. They have proven we can stabilize entanglement, then use it to extract structure from the world. Error correction, calibration, and cryogenic engineering become part of the argument, because they show that fragile quantum states can be shepherded rather than merely observed. So the terrifying implication is narrower and sharper, and it lands with the weight of restraint. If the universe computes, our machines are not imitations. They're small, cold experiments inside the same substrate that shapes space-time. Each run is a negotiation with entropy, with vacuum structure, and with the limits of what can be known locally. Next, we follow that change outward. If quantum computation is a window into cosmic structure, the final chapter asks what counts as one world. Bell violations, repeated and loophole closed, rule out local hidden variables as reality's engine. In labs from Aspect's early photon tests to modern cosmic and satellite runs, the correlations arrive too strong and too coordinated for any purely local story. Superposition and entanglement are operationally real because engineered interference keeps paying out in statistics. On screen, fringes sharpen, phase knobs turn, and coincidence counts rise and fall like a metronome that refuses classical explanation. Quantum error correction proves scalable control of quantum information using measurement without learning the protected state. The trick is indirect. Syndrome checks expose which error happened, while the logical qubit stays hidden behind redundancy and careful decoding. This pushes the documentary toward its climax. Interpretations remain underdetermined, since many worlds, collapse, boom, and epistemic views match circuit outcomes. Quantum performance alone cannot select one story, even when classical verification fails and the device becomes its own opaque witness. The terrifying pivot is practical. Quantum theory is a macroscopic engineering substrate that can outrun auditing, reshape security, and concentrate power. If the universe is a quantum state, reality may resemble an evolving wave function, not one definite world. Next, we follow that question inward. As machines scale, do they extend technology or force discovery that reality is information across parallel possibilities? We began in rooms colder than deep space, where engineers built a paradoxical machine, a fortress against the universe and a microphone for its faintest whispers. By suppressing heat, vibration, stray light, magnetic drift, and even cosmic rays, they kept phase alive long enough for interference to do real work. That work is not philosophical. It is metronomic, as superposition and entanglement become industrial resources rather than laboratory curiosities. Across a century of impossible experiments, the story kept tightening its constraints around reality's throat, from Planck's quantized energy to Einstein's photons, from Bohr's spectral rungs to the uncertainty that refused to be ignorance. Bell then turned metaphysics into accounting, and every loophole-free violation told us the same unsettling thing: the world cannot be explained by local hidden parts carrying pre-written answers. Entanglement survived not only across benches and basements, but across cities and satellites, obeying no signalling while still coordinating outcomes beyond any classical bargain. Quantum computing raised the stakes by scaling that coordination into many-qubit states, where the honest description grows like 2 to the n and quickly outruns any classical notebook. The outputs still look mundane: bit strings, histograms, simple counts, yet the path to them can become inaccessible to classical reconstruction. That mismatch created the verification crisis we kept returning to, because science prefers predictions it can rederive, not miracles it can only observe. So the field built a new standard of trust, one that looks less like a single decisive proof and more like a lattice of constraints: cross-entropy benchmarks, heavy output tests, calibration ladders, spoofing checks, and complexity arguments do not explain the device, they corner it. Error correction went further, turning measurement into a controlled tool, extracting syndromes without extracting the secret itself, and proving that fragile quantum information can be stabilized by redundancy and decoding. And then the implications widened beyond the lab, because computation is not free, it is thermodynamics with a ledger. Landauer's price for erasure ties logic to heat, and quantum field theory ties emptiness to structure, making information feel less like a metaphor and more like a cosmic ingredient. If inflation amplified quantum fluctuations into galaxies, and if entanglement can behave like geometry scaffolding, then our cryogenic processors are not just gadgets. They are deliberate disturbances of the same substrate that shape the sky. Yet none of this, by itself, selects a single story about what is really happening. Many worlds, collapse models, Bohmian trajectories, and epistemic readings can agree on the same statistics, even when those statistics are too hard to classically replay in full detail. As the machines become opaque witnesses, what we can certify is